Let's talk about a very important topic called stacks and queues. Stacks and queues is one of the most important topic when it comes to computers programming. Recursion, for example, is based on stacks. Understanding stacks enables you to better understand how recursion works internally, and hence you can use it to optimize space of your program as well. It's extremely important for interviews. You can expect direct questions on stacks or queues. For example, if you want to find the maximum area under a histogram, you can do it using stack. The parentheses problem as well can be solved using stack. The sliding window problem can be solved using a queue. So these are important from an interview perspective. But having said that, it's also important for day-to-day activities as well. Why? You might have heard about Kafka or Redis queues. These are nothing but the data structure queue, right? At a massive distributed scale. So these are not just important in terms of an interview, these are also important in day-to-day activities as well. Hence, do not skip these topics.
Okay, so today we are going to cover stacks. So let me give you first a little introduction about stack. So first of all, the stack is very much important. It's the most favorite topic of the interviewers. Be well versed with this topic. Like first go through the basics, understand it because they are very straightforward, and then attempt as many questions as you can. There are some standard problems that you should definitely attempt. That was the gist about stacks. Now let's get started. Cool. So stack is very much similar to the stack of objects you see around yourself. So be it stack of plates, stack of books, so stack of plates, stack of books, then stack of, let's say, bowls. So you see it and use it every day, right? So let me draw the stack of plates. So this is how a stack of plates look like. Now from this stack of plate, you can insert a plate only from this end, that is top, right? You can only insert a plate on top, and you can only remove a plate from top. You cannot insert or remove a plate from in between because that will disturb all the plates, right? So you cannot do that. You can only remove and insert a plate only from top. So that's essentially the idea behind stack, that we can only insert an item from top and we can only remove an item from top. Okay, so conceptually or logically, you can think of a stack like this, where one end is open and three ends are closed. So from only this end, we are going to perform operations, that is to remove an item and to insert an item. As I was saying, that we can only insert an element from one end and remove an element from that end only, and therefore stack is known as lifo data structure. That is the last, as you can see the stack of plates over here. So this plate which was inserted at the very end will be the first one to come out. That is last in, first out. Okay, cool. So first what we are going to do, we are going to understand stack as an abstract data structure, that is ADT, abstract data structure. What do we mean by abstract data structure? In which the implementation details are hidden, but the operations are given to us. Okay, so let me write it over here, that implementation hidden. Okay, it's not there, it's not given, but only the operations are there. Only the operations are there with which, using which we can use the stack. Okay, so for example, you can see the fan on top of you, right? So you don't know how it's working internally. All you care about its operation, as in you put down the switch and it turns on, and you put off the switch and it turns off. That's what you care about. So that's an abstract. Cool. So we are given, let us understand the basic operations that are available with stack. Okay, so there are 4 basic operations. The first one, I am sure you guys if you know about stack, you must know about all these operations. So that is push function, and then second is pop, the third is top, and the fourth is empty. Okay, so the push operation actually helps us to push an element on the top of stack. So this pushes an element on top of stack. Then here we have pop. So pop removes an element from top of stack. Then we have top, so it returns the element present on top of stack. So whatever element is present on top of stack, it just simply returns it. Okay, so don't worry, we are going to see an example over here. Is empty is the function that tells us if the stack is empty. So if the stack is empty, it returns true, else it returns false. Okay, so these are the four operations, that is push, pop, top, and is empty. Push pushes an element on top of stack, pop removes an element from top of stack, top tells what is on top of stack, and is empty returns true if stack is empty, else it returns false. Remember that pop simply removes an element and top does not remove an element. It simply tells what is present on top of stack. Is it clear now? Okay, so basically while performing a question, you will have to use in C++, let's say you can use STL, right? In STL you have stack. So in C++, you declare a stack like this. You can use a stack like this, and on this object basically you can call all these functions. So push x, then s.pop, and so on. Likewise in Java, you have collections using which you can use stack. So while attempting a question, you don't have to implement a stack of your own until and unless told. Okay, so but in a while we are also going to see how to implement a stack. We are going to actually implement these operations. Okay, cool. Okay, so let's actually see a dry run of these functions. So here this is a stack, and these are the operations that I would want to perform: push 2, push 1, push -1, push 5, then pop, pop is empty, top. So let's perform these functions. Okay, so it's push 2. So what we'll do, from where we'll put it? We'll put it from here. So basically 2 will come over here. Then it's push 1. So 1 will come over here. Then -1, -1 will come over here. Then there is 5, 5 will come over here. Then we are popping. So 5 will be gone, right? 5 will be gone. So we have removed 5. Now again pop is there. So -1 will be gone. So we have removed -1. Okay. Then we are checking, is the stack empty? What will it return? What will this return? It will return false because the stack is not empty, right? The stack is not empty. Okay, so now there is top. So what will be the top function return? It will return whatever is present on top of stack. So basically top is pointing over here. So whatever is on top of stack, it will return that. So it will return 1, right? It will return 1. So that was a simple dry run of how can we use these operations. Okay, how these operations work. Now let us come to the applications of stack, which are very important. Applications of stack. So some of the applications are undo, redo. Then we have arithmetic expression, evaluation, right? Then we have recursion. So these are some of the, then we have string reversal and so on. So these are some of the applications of stack which are very important and you must know. So try to figure out that how a stack can be used in these operations. You know, that's an activity for you, that do try to search that how we can perform an undo, redo. So this is actually present in your browser, right? So whenever you go to any page, from any page and want to come back, so basically you store, for example, let me give you an example. So you are at link, let's say 1, then you go to link 2, then you go to link 3, and you want to come back to link 2. So what you can do, you can actually maintain a stack of them. So like first you are on link 1, you can put it on a stack, link 1. Then you are going to link 2. So put it on top of stack. Then you are going to link 3. Then put it on top of stack. Now you want to come back to link 2. So what you can do, you can simply remove this. And now you are back to link 2. Does that make sense? So likewise, you can also have a redo stack. Okay, so that's an activity for you, that how you can perform a redo operation. Okay, so likewise try to figure out. And we have arithmetic expression evaluation. So I think you all must be very much familiar with this. That is, converting to infix to prefix or postfix, then evaluating the postfix notation. So that's where you can use stacks. Okay, and then you have recursion. Stack is a core of recursion. So you make function calls, and when you come back, so that basically those function calls get stored on top of stack. Okay, likewise string reversal. Okay, so there is another application that you may be using in your daily life. You must have seen this InShots app, right? So what happens in this, you are on this screen, okay, and so here I am actually at my feed. I am at my feed, okay, and I am watching this news. So I can only see another news if I remove it, if I remove this. So can you see that how this is an implementation of stack, right guys? Now let's talk about the implementation of stack. So could you guys tell me how can we implement a stack? So using arrays, second is using linked list. Okay, so how can we implement a stack using arrays? So basically, let's see. So we can have an array. So size of the array is, so array is A, and size of the array is 7. Okay, so what we can do, so let's say I want to push 2, push 3, push -1, pop, push 7, pop. Let's see how can we implement these operations using stack. Okay, so what we can do, basically we can actually enforce that one end of the stack will be there to perform all the operation. So you can imagine it like we are pushing the elements from here and removing the elements from here. So let's say I want to push 2, so 2 comes over here. Now you can also maintain a top variable which is right now pointing over here. That means what is on top of stack? 2 is on top of stack. Then we have push 3. So what we can do? We can simply increment this top variable and push 3 in here. Then push -1. So we can simply increment this top variable and push -1. Now how to pop it? How can we pop it? Top minus minus. So basically we are now at index 1 and we have, so basically -1 is gone. Okay, then we are at, so this was done, then we are at 7. So again we can increment the value of top and 7 comes over here. Now again pop's coming, so we can come over here and this is gone. So basically that's how we can operate a stack using arrays. Okay, and now can someone tell me the problem of stacks? So problems of stack are, which are very important if let's say an interviewer asks you to implement a stack using arrays or linked list. So if I talk about arrays, then we have problems, overflow and underflow. Let's say I want to push 1, 4, 0, 5, 6. These are the items that I would want to push. So 1 comes over here, then 4 comes over here, then 0 comes, then 5 comes, then 6 comes, and now I would also want to insert, let's say, -1. So as you can see, as I move my pointer forward, there is no space because array has a fixed space, right? So I cannot insert any more element, and that leads to the condition of overflow. Okay, and it's very important. So if interviewer has asked you, he's basically maybe judging you that will you cover these cases or not. Okay, so this is the thing. So how can you handle it? So basically here you have mentioned a size, right? You can keep a check that if size, so if top is equal to the size -1, so in that case, that's an overflow. You cannot insert any more elements. So that's a drawback of arrays. And to overcome that, basically you can use something known as dynamic arrays. Okay, you can use something known as dynamic arrays. Okay, now let's say I want to pop, I'm calling pop 7 times. Okay, so basically this is gone, third time, fourth time, fifth time, sixth time, and seventh time, and now I am again calling. So now what will happen? Will I be able to pop any more element? No, I will not be able to pop any more element because the stack is empty. So if I attempt to do so, that will lead to underflow condition. So how can you make it all right? Basically, you can put a check that if top, so if top is equal to, let's say, -1, then print underflow. Okay, and simply return. So that's how you can manage underflow and overflow condition. Does that make sense, guys? Underflow is when you are trying to pop an element when there doesn't exist. When you are popping an element when there is no element. So how will you be able to pop? Will you be able to pop? No, right? So that's the case of underflow. So you can manage the case of underflow by checking that if top is equal to -1, that means you have no element, so you simply print underflow and return. Cool. So let's talk about linked list. So in linked list, what you can do is, so you have nodes in linked list where this is the data part and this is the address part. So basically, the nodes of the linked list can be present anywhere in the memory, right? Like array, you don't have everything in a contiguous manner. Everything is scattered. Every node is scattered in linked list. Basically, if you have this as a memory, so if let's say one node is present over here, another node can be present over here. Okay, third node can be present over here. So basically, this address field actually links node. So basically, this will be linked to, let's say, this, then this is getting linked to this, and so on. That's how we store data in linked list. So basically, let's say you have 2 and 1 right now. Then you want to insert, you want to push, let's say, 7. So how you can do? Right now, top is here. So at what position, if you, so you are actually, remember, you are actually implementing stack using linked list. Where would you want to insert this node? This is your linked list. This is what you are building. This is the temp node, current node, that you new node that you want to insert into your linked list. So where will you insert it? That we can actually put it on top of head. So now we can actually make this its next pointer point over here. So this is how our stack would look like. Now top will be over here. Okay? So you can, in case of a linked list, you can imagine a stack like this. Like this, it's growing, right? Like this is it's growing. And when you want to pop an element, so basically you can actually shift this top to the next position, and this will be, so basically you can free up this space. Okay, so that's how you can implement a stack using linked list. Now with linked list, the concept of space, a lot of space is used in linked list. Okay, so basically you are storing pointers as well, that will take a lot of space. And pros of both stack and cons is that you will be able to perform push and pop operation in just order of 1 time complexity. Okay, in just order of 1 time complexity. Okay, cool. Let's get to the question. Okay, so the first question that we have is of very much famous question and very much asked question. It's of valid parenthesis. Okay, valid parenthesis. So the question says that you are given brackets, the round brackets, okay, and you have to tell whether the parentheses are balanced or not. Let's say you are building this compiler in which you will be writing your code, right? So basically you will be you want your compiler to check, verify your code. So in that case you will definitely want how can we check if the bracket are valid or not. So how can we do that? Let's see. First of all, let me give you some examples. Let me write down the examples. Okay, so what do you say about the very first parenthesis? What do you say about the very first parenthesis? Are these set balanced? Is it balanced? Yes, it is balanced because a corresponding opening bracket has a corresponding closing bracket. So yes, it's balanced. Then if I talk about this, is it balanced? No, it's not, because this is complete. They are balanced, but here this opening parenthesis is lacking a closing parenthesis, or you can also say that this parenthesis is lacking a closing parenthesis. So this is not balanced. This is not balanced. Likewise for this, so this is lacking an opening bracket, or you can also say that this is lacking an opening bracket. So this is also not balanced. Okay, so you have to basically tell, are the parentheses balanced or not? Let's say we want to attempt this question without star. Can anyone think of something? Okay, so let me first actually put some observations. Let's do the question step by step. Okay, let's do the question step by step. So observations are, the first observation is that, can an opening bracket make a string invalid? As in, let's say I'm traversing the string and I find an opening bracket. So can that opening bracket make the string invalid? Well, it depends upon the future. It depends upon the future, that if I have this opening bracket, maybe in future I'll find a closing bracket and that will be valid. Or let's say I don't find a corresponding closing bracket, in that case it will be invalid. So it totally depends. It totally depends if I get an opening bracket. Okay. Now if I talk about a closing bracket, so what about a closing bracket? Can a closing bracket be a problem to us if we encounter it? Well, so if till now for a closing bracket there was no opening bracket, in that case, yes, it is a problem, because even if we move any further, the string that is given to us will not be valid in any case, right? In any case. So basically, let's actually okay, let's take look at it like this. So I have something like this. So what will happen? Let it be like this. So I am at here. I will maintain, what I can do, I can maintain a left and right count, which can be initialized to 0. Now I am at an opening bracket. So that means left actually tells a opening bracket and right tells the count of a closing bracket. So I found an opening bracket. This becomes 1. And so let this be the thing. Let this be the bracket. Now I am here. Now I am here. So what I can do? I can simply decrement the value of this, and that will tell us that we actually found a match for an opening bracket. We actually found a match for an opening bracket. So we can actually set this to 0. Right. Now let's say I have a string like this. What will happen? What will happen? That I am here, left and right. So basically I have left 1, then I have a closing bracket. So initially both are 0. So now this is a closing bracket. So is left greater than 0? Yes, it is. That means there is an opening bracket. So we can simply decrement it, telling that we have found a match. Now next we go to the next character. This is a closing bracket. Okay. So what's the value of left? It's 0. That means there's no opening bracket. In that case, we will simply return that it's invalid, because at this point there is no use to move any forward, because this closing bracket does not have a matching opening bracket. So we can simply return from here. Does that make sense to everyone? Okay, so whosoever is saying that can we count the number of opening bracket and the closing bracket? Guys, we cannot simply count the number of closing bracket or opening bracket. Okay, let's take an example of that. Let's say I have this as a string. So now left is equal to 2, right is equal to 2. But are they valid? Are they valid? No, they are not valid because they are not placed in the correct order. Therefore, this is not a right approach. Is that cool? The time complexity of the approach is what? What's the time complexity of the approach? So if we have this case, here the number of opening brackets, closing brackets are 2, number of opening brackets are 2. So are they valid? No, they are not valid. So this is wrong. This way is wrong. So what's the time complexity, guys? Time complexity is just order of length of the string because we are iterating the string just once. And what's the space complexity? Just order of 1. We have not used any space. Okay? We have not used any space. Now, let me make a question little trickier. Now, let's say I have brackets these and these. So, this is an extension of the question. Extension hai ye question ka. Now, I am saying that I have these 3 sets of parentheses. Now, I have to tell, basically, my string can contain these set. So, I have to tell if those are valid or not. Let's take an example. Examples can be this, then we have this. So this will be given to you. Now you have to tell are they valid or not. Now how can you do it? How can you do it? So whenever in the interview you're telling the interviewer that okay, we can use stack for this, but she or he already knows, right? You have to get to it. Like how? What's the intuition? So that's is very important. Okay. Some of you are saying that we can use 3 variables. So that will be wrong because then you won't be able to actually find the order. You cannot judge the order by taking that many variables. So first of all, I am sure that you guys understand that it cannot happen by taking just the left count and the right count, because if okay, so first of all, let's take the example of this. Now here left is 1, okay, and now I find a closing bracket, but here they are not same, right? So this will not work. Having left and right is a bad idea. Now taking 3 variables. So here I have this string. So if I take 3 variables, let's say round, or let me write first bracket, second bracket, third bracket. Now here the first type. So this is type 1, type 2, type 3. First bracket का left right, इसका left right, then इसका left right. First का left is 1, okay. Third का left is 1, okay. First का right, so we have found a right bracket and this manages to be 0. Then we have third ka right, so this becomes 0. But is this valid? No, it's not valid because the order is different. Order doesn't match. So therefore, that's a bad choice. Does that make sense? You should have a clear idea that why your approach is wrong. You should take as many, like if you are stuck, you are not able to think, take examples and try to generalize it. You guys are clear with it? Cool. So let's move forward. Now let's actually build some intuition of this. So one thing is that, let's consider these brackets. One thing is that since, okay, so this is invalid, right? This is invalid. This is also invalid, right? This is also invalid. This is valid. This is valid. They have right set of pairs. Now this is also, this is what? This is what? This is also valid. Okay. This is also, as you can see, that this is also valid. So if I talk about this string, then it's a property of the valid parenthesis that if the complete parentheses are balanced, then their sub parentheses will also be balanced. As you can see that this is balanced, this is also balanced. This is also balanced. So we are not considering all the substrings, right? We cannot consider anything like this or something. We have to choose the right set. But what it means is that whatever the parentheses are inside it, they will be balanced anyhow. So this is its corresponding pair. Then we have this, it's correct, then it's correct, then this is there. So does that make sense? That inside of it parentheses are balanced? Now, so an opening bracket does not bother us, right? An opening bracket does not bother us because in future we may find a closing bracket for it, right? But let's suppose I am at this closing bracket. Let's suppose I am done with everything and I am at this closing bracket. Now for this closing bracket, this is an opening bracket, this is an opening bracket. Does these brackets are of any use to me? No, they are not. Can I get rid of them? Then that will be great, right? So if I can get rid of them, because they are valid in itself, right? As I told you by this property. So since they are valid, if I can get rid of them, then I can actually find out if this bracket has a matching opening bracket. Okay, so let's actually see a dry run of this using stack, because stack is the data structure that helps us find. Just look at just the past. Okay, just the past. So how and what we can do? We are at this bracket. This is our opening bracket. We'll see about it in future. So push it onto the stack. Then this is an opening bracket. We'll see about it in future. Put it on top of stack. Again an opening bracket. Put it on top of stack. This is a closing bracket. Was there an opening bracket for this? Yes. Where can I see? I can see it on top of stack. If there is a corresponding match for this closing bracket, then I can simply pop it off. Next time here, this is a closing bracket. Does this have a match? And see how nicely we have removed between whatever was presented. That is here, we have removed it. We have removed it. And now we are actually comparing this. Where can we find it? On top of stack. So yes, it has a match. Remove it. So now we are here. Now we are here. Put it. So this is our closing bracket. Yes, match found. So remove it. Remove it from top of stack. Then we have an opening bracket. Push it on top of stack. Okay. Then we have a closing bracket. Is the corresponding opening bracket present? Yes, it is present. Remove it from top of stack. Now we are at the last bracket. Is the corresponding opening bracket present? See here how we have gotten rid of all of this, right? So basically, yes, it's present. From where we can find? On top of stack. Just remove it. What's the condition we have to check for validity? And if the stack is empty, then return true, right? If the stack is empty, return true. But if the stack is not empty, so we have to return false. That tells, even after iterating the string, let's say we have completely iterated the string, even if the stack is not empty, so we will have to return false, right? Because there are still left some unmatched opening brackets. So at any time, let's say you have something like this. So at any time you don't find, so okay, let's do a dry run of this as well. So this is an opening bracket, move ahead, opening bracket, move ahead, closing bracket, but no corresponding match. Simply return from here. Simply return from here. Okay, so now let's move on to the next question. But before that, let's talk about the time complexity. The time complexity of this approach is just order of n, because we are going to each and every bracket not more than twice. How? Once while pushing it and another time while popping it. So that's only 2 into n, which makes it order of n, right? That makes it order of n. And the space complexity is order of n, because in the worst case, we may end up pushing all the brackets in the stack when, let's say, the string was something like this. In that case, you will end up pushing all the brackets in the stack. So the space complexity is order of n. Okay, so I hope that's clear, and we'll quickly move on to our next question. So intuition is that how can we, previously clear up something to get just the, so here as I talked about that step by step we made the intuition, like, sorry, I just removed it. So as I was talking about that, inside of it will also be balanced. So if we can remove it, I will just be able to look at here. That's what I want to do. So we can simply remove it, and that is possible using stack. Okay, so let's move forward quickly. Cool. So question 2, and this is very, very famous question, which is of next greater element. Okay. So question is that, let's suppose you are given an element, you are given the elements in an array. Let's suppose 10, 13, 22, 7. For each of these elements, you have to tell that what is the next greater element to its right. Just the next greater element to its right. So what's the next greater element to the right of 10? It's 13. Okay, it's 13. The next greater element for 13, it's 22. The next, is there any next greater element for 22? No, it's not. So we can put -1 over here. We can put -1 over here. Then we have 7. So next greater of 7 to right of it, it's -1. Nothing is there. Nothing is there. Okay, so let me take, this was example 1. Let me take another example as well. So we have 10, 7, 4, 2, 9, 10, 11, 3, 2. Okay, so what's the next right to the right of 10? It's 11, right? Just greater element on the right of 10. It's 11. Just greater element on the right of 7. It's 9. It's 9. Just greater element to the right of 4. 9 again. To the right of 2. 9. Just to the right of 9. It's 10. Just to the right of 10. 11. Just to the right of 11. Nothing. To the right of 3. Nothing. To the right of 2. Nothing. Okay? Okay, cool. See, if you are implementing any question, you can use STL in C++ or collections in Java. You don't have to implement push pop functions on your own. That's just for the sake of if let's say your interviewer asks you. That's it. Okay, that's it. Cool. So if the question is clear, please tell me that how can we attempt it. At least give me the brute force approach. At least give me the brute force approach. So you will agree with me that brute force is nothing. So brute force is using 2 loops. So you can basically, let me actually write the code for it as well. So the brute force look like that. You can have an answer variable, answer array. Then you can iterate through all the elements from 0 to n-1. Then for those elements, you can again iterate from. So, okay, first you can initialize your result to -1 if let's say you don't find any element. So you can do for j that goes from I plus 1 to n-1. You can check if a of I is, so a of I is less than a of j, then simply put answer I is equal to aj, okay, and break from here. Take a break from here because you just have to find just the larger element. You don't have to iterate any further. Okay. Now what you have to do? Actually, this should be result, and out of this for loop, you can set answer I is equal to result. Does that make sense? This is just the brute force approach. Okay, cool. Let's go ahead. So the time complexity of this approach is order of n square, since there are 2 nested for loops, and the space complexity would be order of n, which we can ignore because that will be just to store the, so basically this is just so we can actually make it order of 1 only, because we anyway have to take an answer array. Answer array we anyway have to take because that's how we are going to return the answer. So the space complexity for this we can assume to be order of 1, right? Cool. Now let's talk about the optimized approach, and let's build some intuition for that. Let's see some observation. The first observation is that let's suppose the array elements are 12, 10, 9, 8, 7. Okay? 0, 1, 2, 3, 4, If let's suppose these were the elements, what is going to be the answer for them? What's going to be the answer for 12? Minus 1. Nothing is on right. For this, minus 1. For this, minus 1. Minus 1. Minus 1. Does that make sense? The answer for all of them will be minus 1. Now let's talk about another example. Let's say we have 5, 4, 3, 2 and 10. Now can someone tell me what is going to be the answer for 5 now? For 5 it's going to be 10. For 4 it's going to be 10. 3, 10, 2, 10, 10 minus 1. Does that make sense, guys? Cool. So the thing is that as you can see, when the sequence was in decreasing order, we got minus 1 for them. And here we also had a sequence in decreasing order. But once we got an element which was greater than them, so this element was greater than these elements, so the answer for them became 10. The answer for them became 10. Look at it like this. So let's suppose I have a 5, 4, 3, 2, 10. So I start from here. This is 5, then this is 4, this is 3, this is 2. Now 10 came. So once the number came which was out of order and greater than them, so answer for them became 10. Okay, answer for them became 10. Let's look at one more example. We have 9, 6, 5, 4, 8. So this is 9, this is 6, this is 5, 4, then 8 came. So 8 is 8 to whichever element it is greater, it will become the answer to them. That is here. So this is 9, this is 6, this is 5, this is 4, this is 8. So 8 will become the answer for 6, 5 and 4. Okay? So basically now once we have got the answer for them, can I just ignore this and start by finding the answer for these now? Does that make sense? Does that make sense? Okay, giving you some intuition that here we are also ignoring whatever was redundant from the past. The idea here is that we have a monotonic sequence. We have a monotonic sequence over here. Monotonic sequence is when we have a decreasing or increasing sequence. So my point is that I had a decreasing sequence. Once I find an element out of order, so all the elements which are smaller to this will be the answer for them. This will be the answer for them. Okay? Now, so basically, let's say I have elements 11, 4, 3, 2, 10, 12. So I have 11, then I have 4, then I have 3, 2, 11, 4, 3, 2. Now 10 comes. Now 10 comes. So 10 is greater than these numbers. So answer for these will be 10. Answer for these will be 10. Now since we have got the answer for them, we can actually remove this. We can actually remove this, and now it will become such a sequence. It will become such a sequence. Now 12 comes. So this will come over here. Now whatever is smaller than answer to them, 12 will become the answer. So 12 will come over here and 12 will come over here. Now only. So we have got the answer for them. So we will remove it. And now we are just left with 12. We have completely iterated the array, and whatever we are left with, to them the answer will be minus 1. Minus 1. Okay. So since we are ignoring whatever is redundant to us previously, and since this is a monotonic sequence, therefore stack will help us over here. So let's see the dry run using stack. So intuition was that we had to look at the just past, removing this just past. So whatever answer we had got, we will just ignore them, and now we'll start again from some monotonic sequence like we did over here, over above, right? Okay, so now let us go through the dry run using stack. Then again, if you guys will have some doubt, we will come to those. Okay, so I have 11, put it onto the stack. So 11 has been put onto the stack. Then we have 4, put it onto the stack. Then we have 3, put it on top of stack. Then we have 2, put it on top of stack. Then we have 10. Now this, you can see that this is a decreasing order. This is a decreasing order. Now we found an element out of order. So to whatever elements 10 is greater, the answer for them will become 10. So is 10 greater than 2? Yes. So we found the answer for 2. Answer for 2 is 10. Remove it. Is 10 greater than 3? Yes. We found the answer for 3. The answer for 3 becomes 10. Remove it. Now is 10 greater than 4? Yes. So we found the answer for 4. The answer for 4 becomes 10 and simply remove it. Now is 10 greater than 11? No. So simply push 10 onto the top of stack and move ahead Now we are at 12. So on top of stack there is 10. 10 is lesser than 12. So answer for 10 will become 12, right? Answer for 10 will become 12. Now so we are at 12. Is 12 greater than 11? Yes. So answer for 11 becomes 12. Okay? So now nothing is there. Simply insert 12 on top of stack. Now move ahead. So we are done. We are left with no more elements. So whatever is present on top of stack, the answer for them will become -1. So in this case, answer for 12 is -1. Guys, does that make sense? So Anshul says that then in this solution we need to also store index and stack. Anshul, that's what we are going to do. We actually need to store indexes on top of stack because we actually are trying to find the answer for the previous elements that we are done with. So let me quickly show you a dry run of how we can do this using indexes. Okay. So we are having the stack. We will place 0 over here. Then we will place 1, right? Then we will place 2. Then we will place 3. So basically still the array is in decreasing order. Now we found 10. So this 10 is greater than what is present on top of stack. So basically answer for this. So we will write it like this. S dot top. Okay? Because this is the index. So a of 3 is nothing but 2. So 10 is greater than 2. Answer for this has become 10. Then likewise, answer for this will become 10. Element at index 1 is 4, which is lesser than 10. Answer for this becomes 10. Now 11 is not smaller than 10. So we will simply push the index of 10, which is 4. Then we are here. Now this is 12. 12 is greater than a of s dot top. So we will simply mark the answer of a of 4 as 12. So this is 12. Again, so as we remove it, then a of 0 is lesser than 12. Answer for a of 0, that is 11, will be 12. And now whatever is present on stack, whatever is present in stack, you will simply mark their answer as -1. So you will put -1 here. And the time complexity of this approach is order of n. Since we are putting an element and removing an element just twice, so again order of 2 into n, which is nothing but n. And space complexity in the worst case can be, when let's say the complete array is in decreasing order, it will be order of n. So does that make sense to everyone? Okay guys, so we have actually placed the link to the questions for the next questions. Okay, so hope you guys try it, and guys, this was it. I hope you enjoyed it. Cool. Please try them. See ya. Bye-bye.
Hey everyone, in this lesson we will discuss logical view or abstract view of queue data structure. Basically, when we talk about abstraction, we don't go over implementation details. We generally discuss about features and operations. In actual practice, queue is a structure in which whatever goes in first comes out first. So in general, queue is a fifo structure. Whatever goes first, it should go out first. So if we want to construct queue as a data structure, then we need to support both insertion as well as deletion in the queue. In queue, as we need to maintain FIFO property, so both removal as well as insertion should happen from different end. It means if insertion happens in the front, then deletion should happen from the end and vice versa. Let's take an example to understand this thing. Let's say this is the snapshot of the queue at some particular time. Let's say this is the snapshot of the queue. And this is the front element of the queue, and this is the last element of the queue, or you can say as rear element of the queue. Now, So as we can see here that if we want to make an insertion, it should happen at the end of the queue, which we call as the rear or tail of the queue. Likewise, deletion should happen from the start of the queue, which we call front of the queue. As if I want to delete some element, it should be even because this element entered first into the queue. And if I want to insert some element, it should insert here. So this is the snapshot of a queue at some particular time. Okay, so what we have seen here, queue as a abstract data structure, a list or collection with the restriction that insertion can be performed at one end, that is the rear of the queue, and deletion can be performed at other end, that we can say here as the front of the queue. Let's discuss operations in the queue now. If we want to create a queue, what sort of operations that we need to support? The first operation is insertion, which we call enqueue in the terms of a queue, or we can also say it as push operation. We need to push an element into the queue. And also one other operation that we need to support, that is the dequeue, where we need to remove one element from the queue or pop an element from the queue. Now if I want to create an interface for the queue, how it will be like? Let's discuss about that. If I want to create an interface for the queue, it will be something like I need to support these functions. The first function is enqueue, which supports insertion, and the second operation is dequeue, and here I am assuming that queue is maintaining integer elements, but it can be of any type. Okay, and the dequeue operation means delete an element from the queue, and where this return type symbolizes the element that I deleted. It solely depends upon the implementation that whether we want to return that element or not. We can keep it as void as well. That depends upon the implementation. Also, what sort of other things that we may need from the queue? That what is the element which is present at the front, or we can say it as peak. Is my queue empty or not? So these sort of operations that I may need in order to implement a queue. So what we can say that in high level terms, these sort of operations that we need to figure out in order to implement queue. And most of the languages has an inbuilt library which provides the interface, which may vary from language to language. And as a developer, we don't need to worry about the implementation details, and we can create a queue data structures with the help of available functions. As we have seen here that the operations can be enqueue, dequeue, front is empty. Now what we can say also as queue as a container which is open from both ends. As we have seen here that we are entering an element from this side and removing an element from this side. So it is actually an open container where element goes in from one end and element removes from other end. Now let's say we have this operation available in the library. Let's try to simulate queue. Okay, let's say in the starting we have an empty queue and we need to insert an element 2 into the queue. That means as we have an library, so then we can simply call enqueue function of that library and we can insert 2 in our queue. So when we insert 2, it will come from here. Fine. So now as we know that we need to maintain 2 pointers or 2 variables which keeps track of which is my front element as well as which is my rear element, so that the implementation becomes easy. But so if we have only one element in the queue, then both front and rear pointing to 2. Fine. Now let's say we are inserting one more element into the queue, that is 5, and it will go from the rear side, from this side. Now we need to update our front and rear. Let's say internally the library it's handling all those things. Now the rear reaches here and front remains here. Now let's say we have one more operation. Let's say somebody asks one more operation to insert 3 into the queue. Then the snapshot of the queue will be something like this, where the rear is pointing here and front is pointing here. Now let's say somebody asked us to dequeue an element, that means delete an element. As we know that deletion occurs from other end, from this opening of the container. So then our front got updated to 5 and the rear will be 3. So now we have done the simulation part. and we have seen and the queue in a high level way actually. Now let's discuss some real world examples to understand it better. And it is generally used when there is a shared resource that's supposed to serve some request, and resource can handle one request at one time. In such scenarios, it makes more sense to queue up the request, and the request that comes first serves first. Let's consider an example. Let's say we have a printer that is being shared across the network, and it can print only one document at a time. When more than one request comes to it, it cannot say that I cannot serve your request. So what printer will do? It will maintain a queue of requests and serves them one by one as long as there is a request in a queue. It will keep picking up the request one by one. Let's say we have a printer and all these computers, they are requesting to the printer for the request to print a document, but the printer can only print one document at a time. So what the printer will do, it will maintain a queue and store all the requests into the queue. And what it will do now, after serving a request, it will pick an element from the front of the queue and serve that request. In this way, it will manage everything. So this is one of the real world scenario where we can use queue. This is good for the introduction part of the queue. In the next lesson, we will see how we can implement queue. Thanks. Hey everyone, as you can see here that we have already maintained the 8-day streak and we need to maintain a streak. So in today's class, I think we will solve some of the questions of stack and queues. Proceed at that level. Let's solve some questions. Okay, let's solve the very first question. The question is, let's say all three questions of this clever stack. Okay, let's start the question. We have been given an array, and in that array, we need to find the nearest smaller element gi for every element ai in the array, such that the element has an index smaller than I. Okay, let's say we have more boundary. Gi is the element aj is j is greater than I. Okay, the basic question is, for each particular element in the array, we need to figure out the nearest smaller element for that particular element in the array. Okay, let's say this is our array, and for 4, as we can see that no element is less than 4 in the left side, so we have g1 is equal to -1. So for 5, as we can see that the minimum most element for 5 in the left side is 4, so our answer will be 4 for this case. Now if I can see for 2, okay, both 4 and 5 are greater than 2. So for 2 as well, I can see that there is no minimum element in the left hand side. So -1 will be for this as well. Now, okay, similarly, okay, now let's try to solve this question. Okay, how I can solve this question? Let's first think. Okay, for each element, if I do in a brute force way, what I need to do, I will just iterate over all the elements in the left hand side, and I just figured out whether there is an element which is lesser than that particular element. If I figure out that element, then I found the answer. In that way, I can proceed. Let's first copy this example. Okay, okay. Now what we can do, how we can solve this question, let's see. Okay, let's say, let's start from the end. Fine. Okay, let's say in the initially we have an element 8 only. Okay, now as I move ahead, I just found an element 10, and I know that that element is greater than that element. So I haven't find the answer for 8 as well as 10 yet. So what I can do? Okay, now I just figured out 2. Okay, one thing that is clear to me that 2 is smaller than 8 as well as 10. So, okay, so one thing for sure that I can say that 2 will be the answer for both 8 and 10. Okay, so what I can do, I can update my answers and I just need this data point only, because I already figured out the answer for this. So I just need to maintain 2 only. Now let's say I just go into the other element. I have 5. Okay, if I found 5, when I have 2 to which I need to figure out the answer. For 2, I know that 5 won't be the answer. So I haven't found the answer for 2 as well as 5. Now I figured out 4. Now I figured out 4. I can say that, okay, 4 is lesser than 5. So for 5, 4 definitely will be the answer. For sure. But for 2, it won't be the answer. So after then, I need to store these 2 points. Isn't it? So the way if I will do in that way, I will figure out the answer. So what I just think, okay, I am appending the elements, and as I'm appending the elements, I'm checking. And if I need to check the element, what I'm doing, I am just first checking for the last element and then the second last element, and I'm doing in that way, and I'm able to solve this question. If I'm able to do in that way, then it's easy to solve. So I need some sort of data structure which helps me to maintain this information. And that data structure should be something like where I can add the element in the end such that I can also remove the element which I just added in the end. So it should be last in, last out. And we know that stack is that data structure which provides that sort of thing. So I can use stack here and just try to solve in that way. I am able to achieve, because what I am doing, I am adding an element in the stack, and when I just found an element which is lesser, what I am doing, I am just checking with all the elements in this stack, and if I figured out an element which is greater than that element, I'm just removing it to the stack. So only I am adding an element one time into this stack, and I also am removing from this stack only one time. So that means it's kind of order of an algorithm that we just achieved. Okay, let's try to think how we can write code for this question. Okay, let's write the code. Okay, let's try think what are the constraints that we have been given. Okay, we have not been given any constraint, and the thing is, if we haven't find an answer for any element, we need to return -1 for that particular case. Okay, let me first, what I can do, let me first figure out the size. Okay, let me create my answer, which is of size n, and let me have the default value as -1 for each particular element in that particular array, because we haven't find the answer, and we will follow the algorithm as I discussed here so that we will be able to achieve our solution in order of n time. Okay, let's try to think, okay, how I can do that. We just need to iterate. In the last element, I need to move till the first element. In that way, I need a stack data structure to maintain the information as I just discussed. Why? Okay, so now what I can do if I need to question, okay, one thing I need to be sure that, but what will be the edge case? If my stack is empty, or if I have my element which is at the top of my stack, okay, if I figured out an element, okay, which is greater than my top, then that means I haven't found the answer for both of the elements. So I need this data. So I need to push that element into my stack. If that is the case, if that is greater than, that is element is greater than or equal to my that element, so I need to push that element into my stack. Isn't it? Okay, now I'm done here. So I can new. Okay, if there is other case, if the element at my top is greater than AI, if that is the case, then I need to check for how many elements I have found the answer. So let's first just check the edge case, whether my stack is empty or not. While my stack is not empty and my top element in the stack is greater than AI, in that case, what I can do, I know that answer for stack dot top will be equal to AI for sure. You know? And I can safely remove that element because I just figured out the answer for the topmost element in this stack. Now I need not need this data in the future. So I can safely remove it. By the time this thing gets ended, I can say that, okay, now I'm done. Now I can safely add a ith element because I haven't found the answer for ith element yet. And in the end, what I can do, I can return my answer. And let's check once again whether I'm doing in the right direction or not. I am maintaining my answer and I just created an empty stack, and I'm checking if my stack is empty or if it is greater. So then I need to push that element into this because it's of no use. Otherwise, I need to check if my element is lesser. So that means for that topmost element, I just figured out the answer. So what I need to do, okay, in that way, if I just do in that fashion, I can solve. Okay, that seems like a good approach. Let me test. Okay, it's giving me correct answer. So let's submit. Oh, nice. Nice. We have solved this question. Now let's move to the next question. Okay. What will be my next question? Okay, now the next question is I need to figure out the largest rectangle in the histogram. Okay, that is my question. Let me think. Okay, let me first read the question. We have been given an array of integers a of size n, where a represents a histogram. That is, ai denotes height of ith histogram bar, and width of each bar is 1. Okay, let's say we have been given this histogram, and where the height of first bar is 2, and the height of second bar is 1, and height of third bar is 5, and fourth bar is 6, and so on. And above is histogram, and width of each bar is 1. And we have been given heights like that, and we need to figure out the largest rectangle in that histogram. Okay, let me think how we can figure out that thing. Okay, if that is the case, this will be my answer. Okay, they are saying this is my answer, and the answer will be 5 as my height and 2 as my width. So my answer for this will be 10. Okay, so let me just copy this thing. Let's try to think how I can solve this question. Okay, so the question was, we have been given an histogram where the values are 2, 1, 5, 6, 2, 3. Okay, and we have been given histogram like that. Let me first draw the histogram on the paper, and then it's more suitable. Okay, 1, 5. Okay, it will be 5, and then 6, and then 2, and then something 3. Fine. So this will be my answer in this case. So what I can think is, what can be the brute force way to solve this question? One thing is coming to my mind. I can solve it in a way that, okay, let me take all the contiguous segment to solve this question. Okay, and I can take all the contiguous segment of length 1, then length 2, and just try to find the answer for that contiguous segment. Let's say I just take this contiguous segment of first 3 elements, which is 2, 1, and 5. What will be my answer for this contiguous segment? Okay, I know that the width will be equal to 3, but what will be my height in this case? Okay, I can surely say that if I want to build a rectangle, then the height will be the minimum height histogram available in that contiguous length, isn't it? So I can say that the height will be 1. If I do in that way, then I can solve this question. That is fine. Okay, so if I just take in a brute force way, so how much time it will take to me? I need to iterate over every contiguous segment, and to iterate over each contiguous segment, I need to take 2 variables L and R. So it will take order of n square time. And for each contiguous segment, I need to find the minimum most element. So the complexity will go up to n cube. So it doesn't sound me a good solution to solve this question. Can I think something else to make my algorithm better? Okay, let's think what I can do. Okay, let's think. Let's say I have an example, something like this. Okay, let's say this is my example. If I build a histogram, I have 7 here, and I have 8. I have something 6. I have again 8, and I have something again like 7. Okay, if I am just considering all the contiguous segment, I will consider this segment as well, and I will consider this segment as well. I will consider this segment as well. I will definitely consider all the segments. If that is the case, that means, but I know that for all these segments, if in that segment 6 is the part of that segment, then my minimum value will always be 6. Okay, can I use this idea to achieve something? Okay, why I am just iterating over all the contiguous segment? Why not that maximum contiguous segment for 6, which will give me the answer? Because in any way, other contiguous segments are waste for me. That's the waste of computation time. If somehow I just figured out for that particular 6, what will be the maximum contiguous segment if I just consider this element? So one thing I can surely say that, okay, if I just consider this element, how much elements I need to take in the right hand side that I need to consider. Okay, I can consider 8, I can consider 7, but if I have something 5 here, I can't consider that element. Okay, this gives me the idea that what I can do, I can just take the nearest minimum element for a particular element in the right side. Fine, because such that all the elements in between will be greater than 6, and I can consider those elements for this element. And likewise, I can extend my similar approach in the left side as well. So this gives me some idea. If I do in that way, I can solve my problem. Okay, so this gives me the idea what I need to do for each element. For each element, I need to figure out the nearest minimum element in the right hand side as well as in the left hand side. Because I can surely say that this will be the maximum contiguous length for that particular element, which will give me the answers. And if I take any smaller contiguous length for that particular element, they are of no use. And in the previous question, we just solved how to figure out the nearest minimum element for any particular element. And we know that we can solve this using stack in order of n time. We just solved it. Okay, I can use that approach here as well, and I can solve this. And I can solve similar for the right hand side and for the left hand side, and I'm done. That is sounds like a good solution. Let's write the code for this now. Okay, let's write the code for this question. Now let's say this is the case. Let's first try to dry run this. Okay, now for 2, I know that the nearest minimum element for 2 in the right hand side is 1, and in the left hand side I don't have any element. Fine, and so I just end up with the contiguous segment of one element only for 2. So that means for 2 my answer will be just 2. Now if I take 1, now for 1 I can see that for 1 5 is greater, 6 is greater, 2 is greater, 3 is greater. So I can pick all the elements for 1 in the right hand side. That is good. And in the left hand side as well, I can pick all the elements. That sounds like a good thing. So I can do like that. If I do in that way, so for 1, length available will be equal to n. So which is 1, 2, 3, 4, 5, 6 in this case. So my answer will be 6. Now for 5, if I do in similar way, I can see that for 5, the minimum length available, 6 is greater than 5. And okay, I found element 2 which is less than 5. So I can only consider these 2 elements for 5. Now if I just think of an element in the left hand side, I can see that 1 is the minimum element for 5. So I can consider only these 2 elements for 5. So I have a length of 2. Length of 2 for 5. I have a length of 5. So my answer will be 10 if I take 5 as a length. Okay, now if I take 6 as a length, then my area to consider for 6 will be, I can't take this element because this is smaller than 6, and I can't even take this element. So because these 2 elements are the nearest minimum element for 6. So I just have a 1 length for 6. So my answer will be equal to 6 only. Okay, now I consider for 2. If I want to consider for 2, okay, 3 is greater than 2, so I can consider that element. Now if I move into the left hand side, I can see that 6 is greater than 2. Okay, nice. And 5 is also greater than 2. Nice. But 1 is smaller than 2. So the nearest minimum element in the left side for 2 will be 1. So I can consider only these two elements for 2. Fine. So the total elements I can consider for 2 will be these 4 elements. So my length will be 4. So my answer for this case will be 8. Now for 3, let's consider what will my length. Okay, for 3, I can say that for 3, there are no elements available in the right hand side, but let's see what are the elements available to me in the left hand side. Okay, 2 is the nearest minimum element for 3 in the left hand side. So that means I have just of length 1 for 3 and answer will be equal to 3. Okay, I have considered all the elements by using that analogy, and I can see that if I want to consider that element, so I can just get the maximum length of 5, maximum length of 2 for 5. So that means it's okay to do like that, and in the end what I can do, I can find the maximum answer out of them, which is 10. So 10 will be my answer. Nice. If I do in that way, I can figure out the answer. Nice. And I can see that 10 is the answer for this question. Nice. So let's try to write a code for this. But with the simplest code to write the solution for this will be, let's first have a size. Okay, I need two informations for every particular element. What will be the nearest smaller element? For that element in the right hand side, I also need the information, but with the nearest smaller element for that particular element in the left hand side. So I need both the information for any particular element. So let's say I created two vectors. The one of them is storing the smaller in right side. I need that information for all the elements. So I just initialize. I just need the size of n and the what should be the default value. Okay, I know that if for that element I haven't found any element which is lesser than that element in the right hand side, so I can say that okay, let's just say that okay, so in that case I may end up end of my list, so I can safely mark it as n. Okay, because that seems like a good thing. Okay, now I need one more information which is smaller in the left side. I need that information as well. Okay, if I need that information, so I need this information an element, and in similarly I know that if I move into the left side, I haven't found any element which is lesser than this particular element, so I end up with an index of -1 because something like it goes beyond 0 in the left hand side. So I can pick the default value as -1, which seems like a good thing to me. Okay, now let's fill both of these arrays. How we can fill? So this is quite simple. We need a stack for this, because what we need to do, we need to figure out the nearest most element in the right hand side as well as the left hand side. As we discussed in the previous question, we can easily do this by using stack. And let's say I created a stack. Now let's first solve it for the right side. And let's say I need to iterate. Okay, now how we can do that thing? Let's say I consider the edge case. Let's say my stack is empty, or the value available at the top of my stack is actually less than or equal to my current element. If that is the case, so I haven't found the answer for my current element yet, as well as for any element which are at this stack, because I just found an element which is greater than the element present at the top of the stack. So I need this information. So I need to push that element into the stack. So that's the only thing that I can do. So I am done here. So I can continue. Now, if that is not the case, that means what does this means that I am at the top. Okay, I need to first write the edge case. I need to iterate until my stack is not empty, and my stack top is, if it is greater than AI, that means the ith element, it's basically lesser than the topmost element. So I can say that for the topmost element, ith element will be my answer. So as I'm moving into the right side, so I can update the answer for smaller right side, stack dot top. I can safely update it as I. Now I need not need the information for that particular element, so I can easily safely pop that element from my stack. Nice. So if I do in continue that way, I haven't figured out the answer for I yet, so I need this information. So I need to push that element into the stack. Let's say I just push that element in my stack. Fine. If I do similar way for my left side to populate this array, okay, I just need to apply the similar algorithm for this case as well. So what I can do, I just move into the left side now, and my algorithm will be something like this only. So I can just copy the same algorithm. Okay, so if that is the case, so but instead of left side, now I'm populating my left array for each element. Now, by doing these two operations, we just populated both of my arrays. We now have that information that for each particular element, what will be the nearest smaller element in the right side, as well as we have that information what will be the nearest smaller element for a particular element in the left side. We have both the information. Now, let's calculate the answer. Let's say initialize my answer as 0, because obviously my answer will be bigger than that 0, so I can update my answer for each particular element. Now, okay, what I can do, okay, now what I can do for, let I have an element in consideration, which is element in consideration, let's say it is a of I. Now, what will be my temp answer? That temp answer is basically this answer, which symbolizes that if I take this particular element in consideration, what's the maximum area of rectangle that I can achieve? Okay, let's try to think. Maximum rectangle area that I can achieve for that particular element. Okay, for that, my length will be, height will be this, and what will be my width? I know that if I need to figure out the width, I need to find the nearest smaller element in the right side as well as in the left side. So for this, that's why I just keep the default value as -1 for left hand side and n for right hand side, so that it's easy to compute that thing. So let's say for 2, I have my nearest smaller element in the left side will be -1 and in the right side will be 1. So if I take the whole length will be equal to 3. If I take the whole length, my whole length, that is nearest right side minus of particular that element I, and I take the nearest left side, the particular element I plus 1. So this will be the total length. But in that particular length, I just include the nearest smaller element in the right side as well as for the left side. But I don't need to include these two elements, because these two elements shouldn't be included in the rectangle. So I can safely remove -2 to remove these two elements, and I can update my answer as max of my answer and temp answer. If I do in that way, I can easily achieve my answer and I safely return answer in the end. Let's see. Okay, I just initialize my array and I just keep my smaller right side as n. I just add the default value as n. For the smaller left side, I just did in the similar way. I maintain a stack. Okay, we missed one thing. Okay, what we need to do, because there are many elements, after solving it for the right hand side, for that particular elements, we haven't find any elements in the right side which are smaller than that element. So that element still remain into this stack. So I need to remove all that elements from my stack. So I need to remove, let's say I removed that algorithm from my stack. Okay, so now let's look at the complexity part of it. This is running order of n time, this is running order of n time, and also this is running in order of n time. So the overall complexity will be 3n, which I can safely say it as order of n. Okay, nice. So we just solved this question in order of n time. Nice. That sounds like good thing. Now let's test my thing first. Okay. Let's see the errors. We have an error at 51st line. Okay, I guess the error is okay. It's not nearest. It's smaller. A smaller. And is there anything else? Okay. Okay, this is correct. And you need to push. Okay, now let's test it again. Okay, nice. Okay, everything seems correct to me. Let's submit my code. Let's see. Oh, nice. We solved this question. Nice. So now let's look the other question for today. We have solved both this question. Now let's look into this question. But what this question is saying that we have been given an array of integers. This is a sliding window of size b, which is moving from very left of the array to the very right. And you can see that W numbers in the window. Each time the sliding window moves rightwards by one position, and you have to find the maximum for each window. Okay, so the question is, we have been given an array, and in that given array, we have been given a window. We need to figure out the maximum element in that window, and that window is basically a sliding window. So what does it mean? Let me explain you. That let's say we have been given a window of size 3. So in the starting, let's say we consider the first 3 element of the window, and we figure out the maximum, and the maximum value for these particular 3 elements obviously will be equal to 3. As you can see that 1, 3 and -1, the maximum element for this will be 3. Nice. So now let's look at the other thing. Okay, now for if I just take the other next window for this particular case, the next window will be 3, -1 and -3. Nice. So if I take this window, and then I can see that the maximum for this window will be equal to 3. Nice. If I take the next other window, then I can say that the maximum for this window it's equal to 5. Okay. And for this window, if I go in the similar fashion, I can see that, okay, the maximum is 5. And for other window, I can see that the maximum value is 6. If I go in that way, okay, if I take the last window, the maximum value is 7. Okay, so this is my question. How I can solve this question? Okay, let's think. Okay, let me move to here. Now, how we can solve this question? Let's see. Okay, we have been given as some array. Let's say we have been given array. Let's say we pick a random array now. 4, 7, 8, 3, 2, 5, and we have been given b as 4. Let's say this is given to us, and we need to figure out the maximum element in each window of length 4. So the first window will be 4, 7, 8, 3. So the maximum value for this window will be equal to 8. Nice. Now the next window will be this, and again the maximum value is 8. Okay, the next window is this, and the maximum value is 8 again. Okay, how I can solve this question? Let me first think. Okay, I need to consider all the windows. So the brute force way will be, I maintain a window and I just keep one start and end, which is referencing my current window, and I just figure out the maximum element in that particular window and I will get an answer. That's the thing that I can do, and I will achieve and I can solve it. But now let's look at the time complexity to solve this question. Okay, if I maintain one window, that means, what does it mean? It means if I need to find the maximum, okay, one way is what I can do. I can just find the maximum by do the iteration from start to end. But this will lead to other order of n time, and how many updation that I need to do for start end, as there are only order of n windows. As we can see that the first window is of 4 element, then the next window of this 4, and the next window of this 4. So there are only 3 windows, and that's of order basically n. So the overall complexity will be order of n square. Can we improve this algorithm? Is there any way to improve this algorithm? Okay, the one way that we can do to improve our algorithm is, what I can do, I can maintain some sort of structure that we know, and that will tell me the maximum element within a given range. Within a given range, I can do something like that, and maybe that will solve my question. But if I need to maintain that structure, we already know that the segment tree provides that sort of flexibility that gives us the maximum value in a particular range. Okay, and this will solve my problem in order of n to order of log n. If you can use something like that, but even then my complexity will be n log n. Can I improve further if I want to solve this? Let's see. Maybe we can improve it further. Okay, let's say we have been given an example 4, 7, 8, 3, 2, 5. Okay, what we can do? Okay, what I can see here that, okay, let's say the window size is 3. Let's say the window size is 3 in this question. But I can say that, first of all, let me consider the first 3 elements of this window, which are 4, 7, 8. Okay, I just figured out one thing, that if I have only one element, I can store this information. Now I encountered an element which is greater than that element. If that particular element is greater than that particular element, so I can say that this element won't be the answer in any of the window. Why? Because this, I just found an element which is greater than this element and has a greater index as well. So that means if there is a chance that I will just need to remove an element, that will be the element of lesser index, obviously, for sure. And if I just figure out an element which is greater than this, so that's of greater use than this. So I don't need this information. So I can safely remove this information and I can keep this information only. Now, in the similar way, if I figured out 8, okay, I can remove this information as well in a similar way, and I can just store the information 8 only to solve my answer. Okay, if I do in this way, I can solve this question. Okay, let's see. Now my answer is 8 for this. Now, okay, now let's say I now come at 3. If we figure out an element which is lesser than this element, okay, but I can't say anything now. I can't say anything now because there may be a possibility, because it has a larger index, there may be a possibility that for some other window, this will be my answer. So I need to store this data as well. So that means we are coming up with some algorithm. If we are figuring out an element which is greater than any particular element, if that is the case, so we can safely remove the element which is at the end of my some data structure. And if I figure out an element which is smaller than that element, so I just need to append that element in the end. Nice. But one thing we also need to show that if we go in some other window, we need to remove the elements which are not in that window. And as I am just adding all the elements in the increasing order of index in that data structure, in some data structure, so I can just check whether the first element is of previous window or the current window. If it doesn't belong to the current window, I can safely remove that element. So, okay, so one thing that I'm sure that I need, if I want to solve this question by using this algorithm, I need a data structure which will help me in adding in the end, also removing in the end, and also allows me the ability to remove from the front. Okay, and all those operations should be as efficient as possible if I want to make my algorithm faster. So what data structure that comes to my mind? Okay, can I use stack? If I use stack, then these two operations will perform in a good way, but not this. Okay, so what sort of data structure I can use now? Okay, can I use queue? If I use queue, I can do this operation and this operation, but I need to sacrifice over here. Okay, then what other data structure that I can use? If I'm using some complex data structure, then the complexity will be log of n. And we already know that we just build a segment tree rather than that data structure that will already solve us our problem in order of log n. So we need some sort of data structure. Okay, one thing that comes to my mind, why don't we use the doubly linked list? In the doubly linked list, we can add, and we have both the pointers head and tail. We can just add the element, and then we can easily remove the element from the end in order of one time, and add that element in order of one time. And similarly, what we can do this thing in the front as well. If we follow this approach, we make our algorithm efficient. Nice. So in C++, we have this doubly linked list in a form of dequeue. So we can use dequeue in our case and we can solve this question. Nice. So now let's try to look at the example and we'll solve this question again. We have elements 4, 7, 8, 3, 2, 5. Okay, if that is true, now let's try to think. Okay, I have a window of 3 elements. Let's say I maintain a dequeue where if I have a first element, I just put it and I figure out a second element. If it is greater, so 4 is of no use, I can remove that element. So I can put 7, and if of no use, I can remove that element. I can put 8. Now I just end up with the window. What will my answer? It will always be the first element in the dequeue, isn't it? Because the way we are just storing the data, the first element of that window will always give me the answer. So if we do in that way, we can just get the things done, man. That's cool. We can do in that way. Cool. So now if I want to consider a next window, it will be something this. Okay, now let's see what is the index of 8. Index of 8 is 2, but in the current it belongs to the current window, so I not need to remove that element. So what I can do, I can just add 3 here because I need to add 3 because it is lesser than this element and this element can be the answer for other windows. So I need to add 3. Now I am at, okay, I just add 3 and the answer will be again 8. And similarly, if I do it that way, I will find the answer. Now let's try to write the code for this. We figured out everything, what is required, and we just figure out the algorithm to solve this question. Okay, how we will write the code? One thing is clear to you, one thing is clear to us that, okay, let's say first take the size. We need a data structure like dequeue, and let's say it's dequeue. Okay, now I need to iterate over my link, over my array. Okay, let's first do the parts. Let's say first cover the edge cases. If my dequeue is empty, and or if I have an element in the end of my dequeue which is basically greater than my current element, in that case what we need to do, we just figured out in that case we may need this information. So in that case we can add this element in the end and that will help me to solve this question. Now if that is not the case, what we can do, we can check while, okay, my dequeue is not empty and we are getting, okay, we need to add 4 as well. What we can do, if my element in the back, they are lesser or equal to my AI, because I just found an element of greater index and it is greater than the last element of my dequeue. So that means I don't need that last element in my data structure. So I can safely remove that element. Okay, I can do in that way. So in the end, I need that ith element. So I need to add this element in the end. So I am done. But I need to remove all the elements which are not belong to my current window. As we can see that, okay, my next window will start when I becomes greater than or equal to B. So what we need to do in that case, if that is the case, okay, let me first initialize my answer as well. Okay, and so that means if I just end up with an index greater than or equal to B, what does it mean? It means that we just completed our one window. So I can add the answer for that window in my answer vector, which will be the front of my dequeue, as I already discussed why it is, isn't it? So it will be my front. Okay. Now what I can do, if that is the case, now what I need to do, I need to check whether the first element of my data structure is in the current window or not. So for that, first I need to check the base case. If my dequeue is not empty, otherwise it will give us the segmentation fault. And if my dequeue is not empty, and we can say that the element, okay, the index of the element in the front should be, if it is, okay, if it is the first element, it's the 0th element. If I'm at the second window, then the index, if the index is 0, then I can safely remove that element. So the index will be I minus y, because if I at the next window, my I will be b and b minus b will be 0. If I'm at the next window, my I will be b plus 1. So if in the front I have the element which is having index 1, so I can safely remove that element. So if I do it that way, I can easily solve this problem. So if I do it that way, what I can do, I need to remove my element from the front. Okay, if I do in that way, I'm done. Nice. But okay, but what about the last element? What about the last element? When I'm at the last element, I haven't updated the answer for my last element. So I need to update it here. Let's say, okay, that will be, my answer will be dequeue dot front. Okay, I just don't need to add the answer dot front. It will be the element for that. So I need A for that case, A for that case as well. If I do in that way, I think this should work. I need maintain dequeue, I maintain vector. When I do in that way, I'm pushing my answer. I'm considering all the cases. Now let's test. Oh, I need to return answer as well for sure. In that way. Okay, nice. Correct answer. Now let's submit the code. Nice, we solved this question. Now we are already ahead of our streak. We completed the 2-day streak in a really good way. Okay, nice. So this is all about today's lecture. Thank you guys.
Let's talk about trees and understand why trees are important for an engineer. Trees are used to implement other useful data structures like sets and maps. Heaps, priority queues and tries are also based on trees. In fact, indexing in the database is also implemented using trees. The underlying data structure used in text editor, for example, is also based on, you guessed it right, trees. As an engineer, it is must to have a solid foundation on the trees. You should be able to solve all the problems related to trees. Companies like Amazon, Google, Microsoft, Adobe love asking questions on this. In fact, I will go to an extent and say that no Amazon interview is complete without solving a tree problem.
Hello everyone, in this video we are going to start study about an interesting data structure known as trees. Till now you might have heard about data structures like arrays, linked lists, stacks and so on. These data structures are linear data structures. For example, take a linked list. In linked list you have a set of nodes where each node points to the very next node. In this linked list, suppose there are 3 nodes. Let us say this node stores the data 4, this stores 1, this stores 8, and this is an end pointer. What is the start of this linked list? Correct. This node points to the start of the linked list. As you see that in a linked list, there is a logical start, there is a logical end pointer, and also there is a logical meaning of the next element. These are the properties of linear data structures. What is a data structure basically? Data structure is nothing but a way to store and organize data in a computer system. How will you choose which data structure is perfect for a particular problem? You might choose this based upon some different kinds of criteria. The first criteria might be the type of data that you are representing. The other decision might be to reduce cost or time complexity for frequent operations. Example, suppose you are given a problem that hey, we are given a set of numbers and multiple queries where you have to find if a particular number exists in the array or not. What data structure you will use? You can use an sorted array and apply binary search, or you might also use a hash map. Sometimes the choice of data structure is based upon reducing space complexity. Tree is a data structure that is most suited for hierarchical type of data. Consider the organizational hierarchy of a big corporation. There is a CEO. Under the CEO, there might be multiple presidents. Similarly, under each president, there might be multiple vice presidents, and so on. This is a type of data that is one of the most common types of data that can be represented using a tree. Why is it even called a tree, by the way? There is a very similarity between this data and an inverted tree. What are these things in the tree? Yes, these are the leaves. Similarly, in our tree data structure, the end nodes, had there been no other nodes downside it, are known as leaves. What is this in the tree? This is a root. Similarly, the top of the tree data structure is also known as the root of the tree. So basically, a tree data structure represents an inverted tree. Now, let us look at some terminology related to trees. Let me draw a formal tree for an example, and let me number the nodes in some way. 1, 2, 3, 4, 5, 6, 7, 8, 9. The very first terminology that is related to tree is the root of the tree. Root of the tree is nothing but the node which is at the very top of the tree, or the node under which all the other nodes of the tree lie. So in this example, 1 is the root of the tree. Now let us discuss the parent-child relationship. As there is an edge from 7 to 9, 7 is known as the parent of 9. Similarly, 9 is a child of 7. Now, what is the case of 6 and 7? As 6 and 7 have the same parent tree, 6 and 7 are known as siblings. Okay. Now, the very common term that you will see when reading about tree algorithms is a leaf. A leaf is a node that has no child. So, in this example, node 8, node 5, node 6 and node 9 are leaves of the tree because they have no child of themselves. Now consider a path from the root of the tree, that is 1, to a particular node, for example 8. We see that on this path the nodes that lie are 1, 2, 4 and 8. If a node lies on the path from root to a particular node, for example 2 lies on the path from 1 to 8, 2 is an ancestor of 8. Conversely, 8 is descendant of 2. Now we studied about ancestor and descendant. Now let us see for a particular node 8 again. What is the length of the path from 1, that is root, to 8? As we do here, the length of the path from 1 to 8 is 3. The length of the path from root to a particular node is known as depth of a node. In this case, the depth of node 8 is 3. Similarly, what is the depth of node 3? As the length of path from 1, that is root, to 3 is only 1, which means depth of 3 is 1. Similar to depth, there is another term which is height. People tend to confuse between depth and height. As depth is the length of the path from root to a node, height is the length of path from node to farthest leaf in the subtree rooted at node. Let us take the example of node 3. In node 3, what is the subtree rooted at node 3? Correct. This is the subtree that is rooted at node 3. What is the farthest leaf from 3? As you can see that the farthest leaf from 3 is the node 9. So, what is the length of the path from 3 to 9? It is 3, 7, 9. So, the length of path is 2, which means height of node 3 is 2. So make sure you understand the difference between height and depth clearly and don't confuse between those. This was the definition of height of a particular node. Now, what is the height of the tree? Height of the tree is nothing but the height of root node. So, in the example above, what is the height of the root node? Clearly, the longest leaf from the root 1 is 8 or 9. What is the length of the path from 1 to 8? As we saw earlier, it is 3. Thus, the height of tree in the above example is 3. Great. So we have till now discussed some of the terminologies related to trees. Let us discuss a few properties of the trees as well. The very first property of a tree is that a tree with n nodes has n minus 1 edges. Why do you think that is the case? Let us go back to the tree that we draw above. We see that for all the nodes other than the root node, there is an edge pointing to the node. For example, for the case of node 2, there is one edge that is pointing to the 2. Similarly, for node 4, also there is only one edge pointing to the node 4. Similarly, for node 5 and all other nodes. So we see that there is one edge from to any node other than the root. So for n nodes, all nodes other than root have an edge pointing to them. This means there are n minus 1 edges. Based upon the properties of the trees, different types of trees are also defined. So, for example, if all the nodes of a tree have less than or equal to 2 children, this means the tree is a binary tree. Extending this thing, if all the nodes of the tree have less than or equal to n children, implies that the tree is an n-ary tree. Let us take an example. Do you think this particular tree is a binary tree? No, this tree is not a binary tree because we see one node has 3 children. Implies that not binary. Do you think this is a ternary tree? Ternary is also known as 3-ary. We see that this node has 3 children, this node has 1, and all other nodes have 0 child. As we see that all the nodes in the tree have less than or equal to 3 children, this means that this is a ternary tree. Similarly, there are many other properties of the trees of different kinds of trees. For example, there is a binary search tree. We will discuss this in depth in a future video, but as an overview, a binary search tree has a property that all nodes in left subtree of a node have values less than the node value, and all nodes in right subtree have values greater than the node value. Now let us move to some of the applications of this tree data structure. A tree data structure is a very important data structure and is used in many real-life applications. As we discussed earlier, that tree data structure is the by default data structure for hierarchical type of data. So it is used in applications that resemble hierarchical data. Example, the file system of your computer. How is a file system like? There is a parent directory, or which is also known as the root directory. Inside this root directory, you might have multiple other directories and files. For example, this is a directory D1, D2. This might be a file F1. Similarly, there might be another directory D3. Each of those directories can in turn have other directories under them or files. For example, suppose D1 has one more directory inside it and 2 files. A file cannot have anything inside it, so file in a file system will be a leaf node. There might be a directory, for example in this case T2, that might not have anything inside it, which can be an empty directory. I hope it is clear as to why tree data structure is one of the best data structures to represent your file system. The second application of tree data structure is by different types of trees that exist. For example, there is a tree known as trie. Trie is a data structure that is very good to represent dictionary. It allows us to search if a word of length m exists in the dictionary in order of m time. We will study trie in depth in one of our future videos. Similarly, as I talked briefly before, there is a type of tree known as binary search tree. Binary search tree allows us to find if a data exists in the node, exists in the tree in order of height of the tree. That is why you will see that height of the tree is very important factor in analyzing the complexity of tree algorithms, and we will study it in depth also in future videos. One last application of tree that is commonly used is in routing protocols and internet. Are you guys aware of a DNS? A DNS is represented like a tree. Suppose you have to find the address of www.google.com. A DNS server is organized like a tree. There is a root domain dot, inside under which there is a .com, under which there will be a .google, under which there will be www. Similarly, suppose it had to represent facebook.com as well. To represent facebook.com, the root domain will remain the same, .com will also remain the same, but there will be another Facebook here. Great. I hope it is clear as to how a DNS server might now be resolving your queries.
Myself Robin, and we will solve some of the simple questions of tree today. Let's solve some basic questions today. Let's start with the simplest question with the binary trees. Now we have been given a binary tree and we need to figure out whether that given tree is height balanced or not. Okay, what is the definition of height balanced binary tree? It is defined as a binary tree in which the depth of two subtrees of every node never differ by more than one. Okay, I need to return 0 or 1 for this problem. I need to return 0 if my tree is not balanced, and I need to return 1 if the given binary tree is balanced. This is the input that is being given to me, and I need to figure out whether the given binary tree is balanced or not. Okay, as we can see that the height of the left subtree here is just 1, as well as the height of right subtree is also equal to 1. It means that, okay, the difference between the heights for the left and right subtree, it's equal to 0. Okay, if it is 0, that means it is less than 1. So the answer for this case, it should be true. Okay, fine, nice. Now if I just visualize this input, in this input, as we can see that in the left side we have 2 nodes, but in the right side we don't have any node. It means that, okay, the height in the left subtree, it's equal to 2, but the height of the right subtree is 0. So if I take a difference, then the difference for this as a rule, it's equal to 2 minus 0, which is 2. And as it is greater than 1, so that means I need to return false or 0 in this case. Okay, now we got the question. Okay, now let's try to visualize how we can solve this question. Okay, the question is, we have been given a binary tree. Let's say this is the binary tree that is being given to us, and we need to figure out whether that given binary tree is balanced or not. Okay, the simplest thing is kind of a really simple question, that what we can do in this case, I need to first check if that given binary tree is balanced or not. That means that first of all, the left subtree also should be balanced, as well as right subtree also should be balanced. That should be true. If both the things are true, and if I just calculate the height of the left subtree as well as the height of the right subtree, if I figure out height of both the subtrees, then the difference should be less than equal to. If these three cases are true, that means I can say that, okay, that given tree is height balanced. Okay, now if I need to do that, in order to solve for my complete tree, whether that complete tree is height balanced or not, what I need to do, I need to check for my left subtree whether my left subtree is height balanced or not, or as well as my right subtree is height balanced or not. And again, when I just reached at my left subtree, and again I will check whether the left child of left subtree, the left subtree of the left subtree, is balanced or not. Similarly, I will check for the right side, and for here as well, I will check for both the sides. So it seems to me kind of a recursive approach in which the way I can solve this question if I build some sort of recursion. Okay, I need also some sort of information which will help me to evaluate the height in the left side as well as in the right side. Simplest approach that is coming to my mind is what I can do. I can make a function, pass the root, and check whether the left side is balanced or not, or also check whether the right side is balanced or not, and somehow evaluate the height for the left side and evaluate the height for the right side as well, and then just check the difference. And if this gives true, and height is less than equal to 1, in that case I will return true. In other case I will return false. If I just apply that algorithm, that will give me the answer. But now let's try to analyze the complexity of it. Okay, I'm doing some sort of one traversal over the tree, which will cover my recursion part, and also I'm evaluating the heights. Okay, if I will evaluate the height, that means if I am at some node, I need to traverse each level if I want to figure out the height of the given tree. Okay, again, that can go up to order of n. And at each step, I am just figuring out the height. So the complexity in if I solve by this algorithm will be order of n square. Okay, can I do better? Okay, if I want to do better, that means I want to somehow pre-store the height information. Okay, so one approach that is coming to my mind, that what we can do, first evaluate the height of every node. Okay, but then it will take off an extra space. Okay, though, so two solutions comes to us. One of them gives us, solves our question in order of n time, order of n square time, and order of 1 space. And the other solution solves our question in order of n time and order of n space. Can we think of something better? Okay, such that we can solve this question in order of n time and order of 1 space. Okay, let's try to think first. Okay, the point is, just we need to check one thing only, and that thing is basically the difference between the heights of left and right subtrees. Okay, and if I check this information at each level and at for each node, and each node just give me the answer, the difference less than equal to 2, then I am damn sure that that given tree is height balanced. So but one thing that is coming to my mind, that forget about this thing, just try to solve in such a way I can just figure out the heights, because I know that if I want to figure out the height of a tree, it will be, I need to figure out the height of my left subtree as well as I need to figure out the height of my right subtree. So if that is the case, and the height of this will be, because anyways, if I want to calculate the height of a tree, I want to evaluate the height of the left and right subtrees. So the whole recursion part, it can also be covered here. So one thing that I can do, I just evaluate the height of every node, because if I want to evaluate the height of every node, I am checking this condition. I'm doing this thing. So, and I can check whether the difference is less than equal to 1. If it is, that means I am done. That means, okay, if it is greater than 1, that means I just found a node such that that node is not height balanced. If a particular subtree of a given tree is not height balanced, that means I can't say that the whole tree is height balanced. That means the whole tree is also not height balanced. Fine. So I can, the one thing that is coming to my mind, that what I can do, I can keep a one global variable which just track this information. And if I just solve in that way, I am done. Sounds like a good solution. Okay, let's try to solve this now. So the way I think is, so let's first make a global variable is complete tree balanced, and I can initialize the value here for this global variable. It's complete tree height balanced, and I should initialize it with true. Okay, now what I can do, I can calculate the heights for each node, because I know that while I'm calculating the height, I can check the overall height balancing thing. Let's calculate the heights. Let's say first for A, and it should return me integer value. So let's calculate height for a given tree node. This is the case. Now if A, let's try to handle the edge case. If we don't have A, then I need to return 0. Otherwise, the left subtree height, if I need to evaluate, then I need to calculate left height. Again, that function with the left node. If I want to evaluate right subtree height, same function with the right side. I need to follow this procedure, and now I can check this thing. If the difference between left subtree height and right subtree height is less than equal, is greater than 1, that means I'm done. I just found a node, or I found a subtree in more specific sense, that is not balanced. So I can change my global variable is complete tree height balance or not to value false. Nice. If I do in that way, I can surely achieve something, and I need to return the height of that given tree, which will be equal to max of left subtree height or right subtree height plus 1. Nice. If I just solve in that case, and I can return that global variable, because if it is true, I need to return integer. I just need to check if it's complete tree height balanced. I need to return 1, else I need to return 0. That is it. Let me check. I just created a global variable is complete tree height balanced. Okay, now I'm checking the height, calculating the height. The left subtree height is, I'm calling the same recursive function again. And for calculating the right subtree height, again I'm calling the same recursive function again. Now I am checking whether if the difference between the left subtree height and right subtree height is greater than 1, that means I am just updating my variable. Otherwise, I am returning the max of left subtree height and plus 1, adding 1 to it, and I'm initializing it with true, and I'm calculating my height, and I'm done. Nice. Let's submit my code. Nice. Oh, we've already got 261 points. Nice. Let's solve some other question. Okay, he said you took some basic question. Okay, let's try to solve some good question. Let's pick this one. Okay, I don't know, but this, okay. Okay, given the in-order traversal of a Cartesian tree, and we need to construct the tree. Okay, what is Cartesian tree basically? Cartesian tree, it's basically a heap ordered binary tree where the root is greater than all the elements in the subtree. Okay, you may assume that duplicates do not exist in the tree. Okay, nice. So the thing is, we have been given a Cartesian tree, and he cleared me the definition of Cartesian tree as Cartesian tree is basically a heap ordered binary tree. Okay, if it is heap, that means whether the root contain the maximum value of the given tree or it will contain the minimum of the given tree. And it says that the root is greater than all the elements in the subtree. That means root maintains the information that is the maximum value of that given tree. So I need to construct a tree, or I have been given in-order traversal of the tree. Okay, if somebody, or if most of you who don't know about Cartesian tree, let me briefly tell what the Cartesian tree is and all those things. Cartesian tree, it's basically the concept Cartesian tree comes because the thing is it's a kind of BST plus heap, or in some sense we can also call this tree as tree. And the way we have the definition that we have been given a Cartesian tree in that form. That is we have been given the in order part of it, because we know that if the given tree is BST, we can, if we have been given some order, with the some specific in order. Let's say that in order is 1 2 3 4. We can construct so many binary search trees. One of the binary search tree that we can construct is simply 1 2 3 4, because in that given binary search tree the in order is 1 2 3 4, and with the same in order we can construct so many binary search trees. The point is, so the way Cartesian tree comes, it just gives us the unique binary search tree, and that uniqueness comes because of that heap part. Because in that case, why that heap thing helps me, because the way heap we design the tree now such that the root contains the maximum value and it also maintains the in order part. That's the basic property of BST. Okay, let's say we have been given a tree 1 2 3 4. Let's say the maximum value is 4. So I can say that, okay, the 4 should come as a root, and the elements, let's say the elements before after 4 are, let's say the elements are 3.7, 2.8, something like that, and that is the in order. I know that that is the maximum value. That means that, and I need to maintain in order as well. So it means that all the nodes which are less, which has having a index less than 4, that means all these nodes should come into the left subtree. Why? Because I need to maintain in order. I know that the in order of a BST is left root right. If that is the case, that I know that the in order is left root right, it means that, okay, first I need to evaluate left and then root and then right. So I can say that all the nodes after this node will definitely go into the right side, and all the nodes before this node will definitely go into the left side. So we have been given the in order of a tree, and the heap is kind of a max heap. We need to construct that tree. That is our question. The question is quite simple. Okay, let's try to first construct a tree. This question is also not too complex. The point is, we have been given the in order of the given tree in the form of an array. Okay, and I need to construct the tree. Fine. Okay, in this question as well, I can just somehow apply some sort of recursive approach, and in that recursive approach, what I can do, first of all, I have been given a complete vector. What I can do, I just figure out the maximum value in it. Let's say I just figured out the maximum value in it, maximum value in that complete vector, and I just make it as root. And now what I can do, I can just now recursively call for the left side as well as recursively call for the right side. And now what I can do, I can just construct this as a tree as well, and I can mark the left child for this root as the root of the left subtree, and I'll mark the right child of that node as the root of the right subset. If I just solve in that way, then I can solve this question. Now first, before jumping into the code, let's first try to analyze the complexity for this question. Okay, first what I am doing, I am just calculating the maximum value. At each instance, I am calculating the maximum value. Okay, I'm calculating the maximum value which is of kind of order n, and I am calculating the maximum value at each step. Let's say I have a function which gives the root, so it has a node which gives me the root of the tree when it takes a given array. Now what I need to do, first I need to find the maximum element in that given array, and then I need to call the recursive function again. Let's say the index I just got after calculating the maximum value from that given array, it's let's say I. So I need to call the function from the left side to the I minus 1, and that same function again with the I plus 1 to right, because this should go into the right side and this will go into the left side. And what I can do, I can mark the left as this and right as this, and I can return this. Now the complexity is the order of n, just because I am traversing over each of the node, over each element of the array, and also I am figuring out the maximum value in that array as well. So the overall complexity for this solution, it will go up to order of n square. Okay, so we just figured out the solution which is of order n square. Now the point is, can we solve it in a better way? That is the point. Can we solve it in a better way? One thing we just figured out that what we are doing, we are just concerned about the maximum value. Okay, and somehow I know that if that is the maximum value, and so all the nodes here are comes to the left side of it. Okay, let's say I have a sequence. Let's see the sequence. Let's see the example. Let's say we have a given sequence as 5, 4, 8, 3, 1. Okay, if we have that given sequence, what we can do now? As we can see now that we have a 5, and if we just found an element which is lesser than this element, so I can safely say that as 5 is greater than 4, that means the 4 should go to the right side of it, for sure. Okay, now if I figured out 8, now can I say anything if I figured out 8? Now I know that, okay, if I have some elements, let's now try to construct something such that we can able to solve our question in less complexity or better complexity. Now let's try to think what we can do to solve our question in a better complexity. Okay, the thing is, let's say I have 5, nice, then I come across 4. If I come across 4, I know that 4 is less than 5. That means what I need to do, I need to make it as a right child, of 5 for sure. Let's say I just do that operations as well. Let's say I just keep it as right child. Now, okay, do I need the information of 4 ahead? Will it help me in any further processing? Okay, I don't know. Let's see. Let's say I just found the value 8. If I found a value, let's say now 3. After 4, let's say I found a value 3. Now what I can do? Okay, if I found a value 3 and I know that 3 is less than 4 and 3 has a greater index, that means 3 will go into the right side of it. Okay, so I just figured out a solution. If we have been given an Inorder in such way, then I just need to map as a kind of right child of that particular node. Okay, if that is the case, then I am happy. If so, that means I am just keeping the information, and the time I am getting the value which is less than the particular value, in that case I just need to mark it as a right child. Fine. If that is not the case, let's say I am just getting a value which is greater than this value. Let's say I am getting a value which is 4.8. Now, so that means what should be my structure now if this information is given? If this information is given, then I know that, okay, let's say we have 5. I know that all the elements, these are less than these, the elements I am storing here, it's kind of in reverse sorted order. So if it is greater than 3. Nice. So that means all these nodes should go into the left subtree of this, because I need to maintain a heap kind of information. So this particular node should be the root for these two nodes for sure. So what I can do now, the overall structure at the end, it will be something like 5, then the right child 4.8 will come, and in the left subtree I will have 4, and I know that structure. So what I need to do now, what I am just doing now, if I am getting a value which is, let's say I am iterating over the array, if I am getting a value which is less than that particular element, then I am just making that node as a right child of it and just push that something. And if I am getting a value which is greater than this thing, then I just pop all the elements which is in this stack or some data structure, because I just said stack because it is following that property. Why? Because what we are doing, we are adding the elements in the end as well as we are removing the elements from the end. And if we follow the same procedure, somehow we will be able to achieve our solution, isn't it? Does it sound good to everyone? The way I am approaching or the way I am dealing this problem, if I want to achieve it in a better complexity. So the point is, if we follow the same way, we can now the complexity. Now let's try to think about the complexity. If we just try to solve in that way, the thing is, what we are doing, we are just inserting an element in the stack. If that element is lesser than the topmost element of the stack, and I'm marking it as right child of the topmost element, fine. Otherwise, if the given element that I just encountered, it's greater than the topmost element of the stack, then what I need to do, I just need to pop out some of the elements from my stack. Let's say I just popped out these two elements in that case. So the last element which I popped out, I need to keep track of that information about the last element. And I need to make the left child of that particular node as that particular element. And now the topmost element which is present in this stack, I should make that particular node as the right child of that particular node as 4.8. Because in the end, my structure should be something like this, isn't it? If my structure is something like this, only then I can say that that is maintaining some sort of heap information as well as maintaining in order as well. So if I will solve in that way, I can solve my question from order of n square to order of n. Nice. And we know that we can't solve better than this complexity. This is the best complexity that we can achieve for this particular question. Now let's try to solve this question. So as I just told you, we need a stack to maintain all this information. Let's say I created an empty stack, and okay, now let's iterate over my entire array. Let's first keep n as size. Now what I can do, as I know that, okay, let's first check the big edge cases. Let's say if my stack is empty. If my stack is empty, that means I don't have any elements in my current stack. That means that the particular element should be the root. Or if that is the case, or okay, let's first create a root. So that means in that case, let's say my root will be new tree node, and I have been provided a constructor in which I can just pass the value of integer and it will create a root. It will create a node. So I just need that value which is a of I. Nice. And kind of I'm done. Okay, now I figured out the root, and it's better to maintain a stack of tree node. So I can push into my stack, the value of root. Fine. Now the point is, now the case is something like I have an element in the stack, but the current element that I figured out, it is less than the topmost element of this stack. The topmost element of the stack, and I need to just concern about the value of that particular element. So because I am adding the basically nodes into this stack. Now if I just do in that way, in that case what I need to do, first of all let me create a new node. Okay, with the value AI, and mark the right child of the topmost element of the stack as that given node, and I can push that given node into the stack. Fine. Okay, if that, even if that is not the case, that in other case, the other case is I have a value, that means AI is greater than the topmost value of this stack. Then in that case, I need to pop out some elements, and I need to just concerned about the edge case as well. If my stack is not empty and the value at the top, it's basically less than AI, we are happy because we don't have given any duplicates in the tree. So we can do in that way. We shouldn't have to handle the duplicacy case here. So we are good with that. Now, if that is the case, then what I just told you, then I need to keep track of the last element which gets popped out. Because that last element will be the left child of that particular element of AI. Isn't it? So if that is the case, then I can make last, and I can update my last as proto, and I can remove the, I can keep it as null. Okay, now what I can do, I just figured out the last element. So let's first create a new tree node for that particular element. With the value of AI. Now what I can do, the value for that particular node, the left child of that particular node will be my last, and the right child for the topmost element. If let's first check whether we have a topmost element in the stack, or there might be a case that my stack gets empty. So I need to check that thing. If my stack is not empty, then but I need to check whether the, I need to mark the rightmost child for the top as the given. If I just do in that way, I will somehow solve this question. Looks like a good approach to me. And I need to return true. Let's again check the way we think and the way we applied the algorithm. Are they both matching or not? Or have we missed any case or not? Let's first check. Okay, what we do in the starting, we just created a stack and which contains all the nodes. Nice. And we just take our n, which is the size of my array. Nice. I just iterating over my array, and I'm just checking whether my stack is empty. Because I know that stack will be empty, only in that case, I need to push now that element as well. Sorry. I just forgot that thing. Okay. Because if that stack is empty, that means this is the first node, kind of. So that means I need to make it as a, okay. Oh, sorry. I just need to push. Okay. So that means I can't say that it will be my root. The root must be the topmost element in this stack, for sure. But yeah, I need to construct a node here, and I just need to add the node if stack is empty, because I can't do anything else. And the other case will be if we have our value, it is less than the topmost value, then we are sure that in that case, we need to mark it as our right child for that particular element. So we are doing this thing. So it seems right to me. Now the other case will be if AI is less, if it's not less, then it will be greater. So that means it should be the root of some of the nodes. So I'm just checking out all the nodes. So for that, what I'm doing, I'm just checking up till when I have that given value, it's greater than to the topmost value. So I'm just maintaining my last node because it is required. And what I am doing, I am just creating one new node, and just what I am doing, and just mark the left child for that particular node as a last. Nice. If I do in that way, it seems like a good thing. Now let me test. Okay. Oh, sorry. Nice. Let's submit this code. Oh, okay. What's wrong? Let's try to see. Have we done anything wrong here? We have been given the tree as 231. If we have been given tree as 231, first what we can do, what we are inserting 2 here, and it shouldn't be that. It will be the first element. It shouldn't be the last element of this stack. Okay, so I need to maintain the last information. Let's say it as null, because the way we are maintaining our stack, it's in reverse sorted order. If it is in reverse sorted order, what does it mean? That means the maximum value should come in the front of my stack, and I am popping the element in that a way that if we have a maximum element, it won't be go out of my stack, and it will always be appear in the starting of my stack. So I need to update as this, and I need to pop. If I do in that way, then it should work. Sorry. Why now? I'm updating my last here. Okay, not stacking. Sorry, I'm doing some silly mistakes today. Let's check. Nice, we solved this question. It took us some time, but we solved this question in order of n time. That's good. That's good for us. Okay, let's solve one more question today. Let's solve this question. I don't know what's this. Okay, the question is, we have been given 2 binary trees and we need to check whether they are equal or not. Okay, 2 binary trees are considered equal if they are structurally identical and the nodes have the same value. Okay, I need to return 0 or 1 depending upon this. Okay, let's say I have been given this tree and this tree. I just need to check whether both of the trees are equal or not. It's kind of a very simple problem, but I need to check if the both of the trees are equal. That means the node itself will be equal, as well as the left subtree and right subtree, both left subtree and right subtree also should be equal. If all those things are fine, then I can safely say that the both of the trees are identical. To solve this question, it shouldn't take much time. Then what I can just first concerned about the edge case, and you can see that this simple question, it's been asked in Amazon as well. So, but the point is, are we handling all the edge cases? Are we come up with a good solution at one go or not? So, what are the edge cases? What will be the edge cases in this question? The basic edge case for this question will be let's check whether we have been given both the nodes as empty or not. If we have both as empty, both the trees as empty tree, then I can safely return 1. Because I know that in that case, both of the tree are identical. If any of them, if both are not kind of empty, one of them is empty, that means both the trees are not identical. And in that case, I need to return 0. So this will be kind of one more edge case. Now I end up with both the trees such that both the trees has some elements. Now in that case, the idea is very simple, but I need to check whether the basically value for both of them are equal or not. And it is equal, and I say that is the left subtree for both the nodes, are they equal or not? Oh, sorry. I need to concern about the left subtree only. And also we need to check whether the right subtree for both the nodes, are they equal or not? If all these 3 conditions met, then only I can say that both the given tree is identical. Otherwise, both the given trees are not identical. If I just solve in that way, I am done. Sounds like a simple solution to me. Okay. Oh, sorry. Today I'm doing a lot of silly mistakes. Nice. Let's submit our code now. Nice. We got a really good point. गोयल दोनों नॉन नल होने से ट्रू कैसे कह सकते हैं? I didn't say that, Goel. But I just said to you that basically, if both of them are null, only then we are saying that as true. Because in that case, both of the trees are empty. If both of them are non-null, then I am checking. Then I'm checking all the three conditions. Where the first condition is whether the value of the nodes are equal or not. If both the trees needs to be identical, okay, fine.
Hey guys, in this video we are going to talk about the problems of code drift day 1. The topics are binary trees and tries. So let's get started. The first problem is BST sum. The problem description states that the cost of an array ARR is the sum of all the values in the left subtree of the binary search tree formed by inserting the elements of ARR in the order they appear in it. Find the sum of the cost of all the permutations of length A. Since the answer can be large, we need to return it modulo 10 raised to power 9 plus 7. A permutation of length n is an array consisting of n distinct integers from 1 to n in arbitrary order. The problem constraints are n can vary from 1 to 10 raised to power 5. Now let us discuss the problem with an example. Now let us look at this example. We are given A as 3. That means we have an array of length 3 which have elements from 1 to 3, right? So all the elements are 1, 2 and 3. Now the permutations we can make out of these 3 elements are this one, this one, this one, this one, this one, this one. These are all the valid permutations we can make. Okay. Now we need to create binary search trees out of all these permutations. So let's do that now. So the first binary search tree will be, first we have 1 as the element, then we'll insert 1 here, then we'll have 2. For 2 we know 2 is greater than 1, so it will come to the right of 1. Then for 3 we know that 3 is greater than 2, so it will go like this. From 1 3 is greater than 1, so it will be on right of 1. From 2 it is greater than 2, so it will be on right of 2, so 3 will be here. Okay, now let's talk about second binary search tree. In second binary search tree we have 1 3 2, so first we need to insert 1. After that 3 is greater than 1, so 3 will come on right. Then after that we can see that we have element 2 as the last element, so we need to insert 2 here. Now from 1 I know that 2 is greater than 1, so it must be on the right of 1. Okay, from 3 I know that 2 is less than 3, so it must be on left side of 3, so 2 should be here. So in that way we can create binary search trees. For the third one it will look like 2 1 3. Similarly in this fashion we can create all these 6 binary search trees. Now the answer to our problem is sum of all the values on the left subtree of each and every binary search tree, right? So the left subtree of first binary search tree, it has nothing on the left, right? So we don't have to add anything to the answer from this subtree. Now again for second one we don't have anything on the left, so we don't have to add anything here again. Now for third binary search tree we can see that we have one value here, so we need to add 1 to the answer. Let's say our answer variable is stored here and currently it is 1 because of this, right? After that fourth binary search tree have 1 in its left subtree, so I am going to add 1 here as well, so the value will become 2 here. Now for the fifth binary search tree I can see that we have 3 on the left subtree, 2 and 1, that is 3, right? Similarly here as well I can see that we have 3 on the left subtree, so I need to add 6 to the answer, so our total answer will be 8. So that is our final answer in this case. Now let us talk about the solution to this problem. Let's say we are given any binary search tree which is rooted at some integer a, right? Now all the values which are less than a should be on the left subtree of this a. Okay, let's say all those values are x, so all these values should be less than a, right? Similarly what will have on the right subtree? All the values which are greater than a, right? Now from this observation the conclusion that we can draw out is that all the values which are less than a should be present on the left subtree of a, right? So if we have any binary search tree that starts with a and it is some permutation, then I need to add all the values from 1 to a minus 1 to the answer. because all these values will lie on the left subtree of our current binary search tree, right? And as we know, the root of binary search tree is the first element of the array, right? So for each permutation, basically I need to add 1 to a minus 1 to the answer, sum of all these values to the answer. Now again, let us look at this example and try to solve it using the observation we just made. So for the first element, I need to add 1 to 1 minus 1, that is 0, to our answer. Since this range is invalid, we don't need to add anything. For this, again, we don't need to add anything. For this one, I need to add 1 to 1, or basically 1 to the answer. For this, again, I need to add 1 to the answer. For this, I need to add all the values between 1 and 2. So I need to add basically 2 plus 1, 3 to the answer. For this one, again, I need to add 3 to the answer. So the answer of all these permutations will be 3 plus 3 plus 1 plus 1, and that is 8 again, right? So basically, what we can observe here, if I know the root of some array, then I can calculate the answer for this array with a simple formula, right? What I need to do, I need to sum all the values from 1 to a minus 1 if that range is valid. Now the next thing that we need to notice is we are given all the elements from 1 to a, which is a permutation. Then let's say I fix the first element to x, then I have to choose rest of the a minus 1 elements, right? So that I can do in a minus 1 factorial ways, right? So if I fixed my x, I know that I can choose the rest of the elements in a minus 1 factorial ways. So that basically gives us the contribution of this element to the answer. Now for any element x, the sum of all the values from 1 to x minus 1, it will be x into x minus 1 by 2, and I'll multiply it with a minus 1 factorial, because I can have this permutation a minus 1 factorial times with x as the root element, right? Now let us talk about the code. So our formula was we need to iterate from 1 to a, and for each number x, we are using this formula x into x minus 1 by 2, and we are multiplying it with a minus 1 factorial, right? So that is basically what we are doing here. But since we need the answer modulo some number, in this case 10 raised to power 9 plus 7, so instead of dividing by 2, I have already pre-calculated a mod in 2. It is basically the mod inverse of the current number. So instead of dividing by 2, I am basically multiplying by inverse of 2, or 2 raised to power minus 1. Now 2 raised to power minus 1 modulo 10 raised to power 9 plus 7 is stored in this number, right? So now whenever I need to divide, I'll just multiply by this mod in 2. And each time we also need a minus 1 factorial. So we are pre-computing a minus 1 here. Okay, so after pre-computing, what we'll do, we'll run a for loop from 1 to a, and we'll use our formula I into I minus 1. This is divided by 2, right? So that's why we are multiplying with the inverse of 2, and then we are multiplying that value with factorial a minus 1, and then we are taking the mod, and after that we are just adding it to the answer, and then we are returning the answer. So it's quite straightforward. Now let us move on to the second problem. The second problem that we're going to talk about is max base pair, and the prerequisite to this problem is tries. You should know how the tries data structure work. So I'd highly recommend you to learn about tries first. Now the problem description is, you are given an integer array A. There's a function f for two integers x and y with another variable b base, right? Now for calculating the functional value, first convert x and y in base b, and then the ith bit of f x y b will be xi plus yi mod b. You have to return the maximum functional value possible for any pair of elements of array A in base B. Please note that you can take two elements for pair from the same index. Note, array elements are in base 10, and you have to return your answer also in base 10, calculated value from equation in base B. And the problem constraints are, A can vary from 1 to 10 raised to power 6, and each element of the array can vary from 2 to 10 raised to power 6, and the bases can vary from 2 to 9. Now let's talk about this problem with an example. Let's say we are given this example here. We are given an array of length 10, and we are given the base as 3. That means we need to first convert all these elements to base 3. So let's do that first. Now here I have converted each and every element to its base 3 representation. I need to find a pair whose sum is maximum base 3, right? And the sum that we are talking about it, let's say we are given two numbers. Let's say I choose this one 12 and 101. Then how do I need to sum them? I'll write them here 1 2 and 101. So what I'll do, I'll add these two. It will give me 3. I'll add these two, it will give me 1. I'll add this, it will give me 1. Now for each digit I need to again do a modulo by 3. So for 3, if I'll do it modulo 3, it will become 0. 1 modulo 3 will be 1 and 1 modulo 3 will be again 1. So the answer for adding 12 and 101 in this manner I am getting is 110. So that's how we need to add when we are talking about two pairs. Now we need to maximize the answer, right? In this example, we can see that if we take these two pairs, that is 100 and 101, and if I repeat the same procedure that I did here, that is 1 plus 0, that is 1, 0 plus 0 will be 0, 1 plus 1 will be 2. Now doing modulo by 3, it will remain 1, it will remain 0, it will remain 2. So I'll get 201 here. So for this specific case, 201 is the best we can do. Okay, so that's what we need to calculate for any array given to us. And if I convert 201 back to integer, it will be 19. So for this specific case, the answer to our problem is 19. So in this way, we need to solve this problem. Now let us talk about the solution to this problem with the same example. So basically, I have taken that same example. These elements here, they represent the value of 1 to 10 in base 3, right? So we have b equal to 3 here. So what we can do, basically we need to find any pair which can maximize our sum, right? So the first thing that I'll try to maximize is the most significant bit, right? Let's say we are given some number here, 2, 1 and 6. Now if I'll add 1 here, then I'll get 217. But if in the same number I am adding 1 here, I'll get 316, which is way bigger than 217. So basically the whole concept is, first off we'll try to maximize the most significant bit, and then we'll move on to maximize the second most significant bit, and in this manner we'll go from left to right. Now that we know we need to go from MSB to LSB, let's say we are at some number right now. Let's say it is 101. Let's say we are at last number right now. Then what I'll do, I'll try to find any number which can maximize it. Okay, so what is the maximum I can get at the most significant bit right now? The maximum value that I can make at most significant bit is b minus 1, right? That's what I can make. Currently we have 1 here. Then what is the value x that I will add to this most significant bit so that I can make b minus 1, right? That means I need to add b minus 1 minus 1. Okay, that is x, right? So the first thing that I'll try to search for is, do I have any number which is equivalent to b minus 1 minus 1, or basically b minus 2. Okay, so in our case b is 3, so 3 minus 2 is 1. Do I have any number in the third place which is 1? If we look closely into the array, we can see that we have one candidate here. Okay, the third digit of this number is 1, right? So we have just one candidate here, so we'll put 100 here. Why didn't we go further? Because we have only one candidate, right? But let's say we don't have one candidate now. Okay, let's take one more example here. Let's say we are given these 4 values which are in base 3 already, and we need to get the maximum pair I can have for each and every value, right? So let's say I want to maximize this 100. I want to find some pair that can maximize it. So what I'll do, I'll write 100 here. Then I'll go from the most significant bit. Okay, so what is the best I can make out of it? That is b minus 1 or 2. b minus 1 is equal to 2 here. Now what is the number I need to add to 1 which will make it 2? So obviously that number is 1, right? So I'll search for the candidates which have 1 on third place. The first candidate will be this one, second will be this one, third will be this one. All three satisfies the condition, right? Now let's move on to the second most significant bit, or this one. Now the second most significant bit is 0. Now again I'll do the same procedure. I'll try to maximize this 0. So what is the maximum I can get at this position? It is again 2, right? So I'll do the same calculation here. What is the value I can add to x that will make it 2? So I'll see that x equal to 2. So I'll try to find among all the candidates that I have selected, do we have any candidate which have 2 at its second place? So I'll see that I don't have any candidates, right? None of them have 2 at second place. Okay, fair enough. That means we cannot make our second digit equal to 2. Now since I cannot make 2, I'll try to make 1 at first digit, right? So what is the value I'll add to 0 so that I can make 1. So that is 1 obviously. Now I'll try to search for a number which has 1 at its second digit. Okay. Now out of these 3 candidates, I can see that this one and this one has 1 in its second position, right? Now this candidate is also neglected. So now we have 2 candidates which is maximizing my value currently, right? Since we have 2 candidates, let's move on to the last digit. Now again, I'll try to maximize my last digit. In order to maximize it, the best I can do is I'll try to make it 2 first. In order to make it 2, I'll try to find the number which have its last digit as 2, right? Now if I look at my candidates, these two, I don't have any of those values, so I cannot make 2. Now I'll try to make 1. Now again, I'll check which one of these have 1. So I'll see that my last candidate has 1, right? That means this guy can actually maximize my sum while I'm talking about this 100 value. So in this manner, we can solve this problem real quickly. But there's a catch. We need to find these candidates each time, right? For each digit, we need to iterate over all these candidates. But we can do it faster by using prefix trees or tries. So let's do that now. So basically, if we are given some array, what we'll do, we'll iterate from left to right. And let's say we are currently at this element, ith element. Then what we'll do, we'll try to build a try over all the previous elements, and I'll try to maximize my current element using the try I have built on the previous element. Now let us try to build try over these 3 values first. Let's say this is the root node of our try. Then the child at each level a try can have is b. Why? Because we can have values at any position between 0 to b minus 1. I'm going to insert this element first. So it has 1. So let's say this is 1. Then again 1. Then let's say this is again 1. Then 0. Let's say this is 0. Okay. Then I'm going to insert this value. Then it will be like 1. Here 1. Then again 1. Now another 1. Right. Now let's try to add this value. It is 1. Then it's a 0. Then it's a 1. Right. Now this is the try structure that I have built right here. Let's say currently I'm at this value. Then I need to find the optimal pair for it, right? So this is my value right now. So I'll start from MSB, that is 1. Now I will try to make it 2 first. Okay, so I'll search for a 1, and in our try we'll see that we have a node which corresponds to 1. So we'll iterate on that, we'll go there, we'll say okay, we are here now. Now from this node we'll try to check the second digit. Okay, what is our second digit? This is our second digit. We say that we need 2 here. Okay, so from this node I'll try to search for 2, and from this we can clearly see that we don't have any node which corresponds to 2, right? We have just 2 nodes. The first one corresponds to 1, the second one corresponds to 0. Okay, so we cannot make it 2. So now I'll try to make it 1. Now we can see that we have 1 here, so I'll go there. Okay, we can make 1. Okay, now that we are here, now I'll iterate on the last digit. So what is the best I can get at last digit? I'll try to make it 2. So I'll search for 2 here. I won't find any 2's, right? We have only 2 nodes, 0 and 1. So again, I cannot make 2 here as well. So I'll try to search for 1. Now we'll see that we have 1 here. So it will go in this direction. So what is the value that I got? I got 1, 1, 1. So again, I got the same pair 1, 1, 1, right? So in this manner, with the help of try data structure, we can do it efficiently. Now that we got the optimal pair for this element, so we can do it for each and every element of the array by iterating over elements from left to right. So that's how we can solve this problem. For better understanding, let's look at the pseudocode now. Now let us talk about the pseudocode. So let's start off with the solution function. So here is the solution function. We are given an array A and a base B, right? So basically, first we are converting each and every element of the array into its corresponding base B form, and then we are pushing that number to a vector named VEC. After that, we are creating a try node, which is basically the root node, and we are inserting one element. Why so? Because in order to get a pair, we at least need one element already inserted in try, right? After that, basically we are iterating from 1 to n minus 1 here, and what we are doing, we are searching for the best element before the current element which can pair up with our current element. So as we have done already in an example, for 100, this function will return 1 1 1. Okay, after that we are combining that and using another vector. So if we combine these two, I'll get 1 1 plus 0 1 1 1 plus 1 2, and doing it modulo 3, I'll again get 1 1 2, right? So that's what is going to get stored inside this answer vector. After that, I am getting the current answer by converting this digit back to decimal or base 10. Okay, and after that I am checking if this answer is the best answer, then I'll just insert it into the global answer variable, right? And after doing all these things, I am inserting our current element into the try data structure. Okay, so in this fashion we can get the answer, and whatever we get at the end, that will be the maximum optimal answer we can get. Okay, after that we are returning the answer. Now let us quickly see what these functions do. This first function, it converts a number to its base b form and returns a vector. Okay, and this function right here, it basically converts the given vector back to its base 10 decimal representation. Okay, and after that we have the standard try node, and then we have an insert function. In order to understand these functions of tries, you need to understand how actually tries work. And in this function we are basically iterating over the try and trying to find the best we can get for our current element. Okay, and this combine, the last function is this combine function. This basically do this operation. It basically adds up both of those vectors and then do the modulo thing. Okay, and then it returns the answer, which is again a vector. So that's pretty much it, and if you enjoyed the video, please hit the like button and do subscribe. Thank you for watching.